So 11:03 or so. There we go. We will start at about 11:03 to give people time to filter in from the coffee break, given that we have 3 talks in this quite long session. All right, folks, welcome to the Static Analysis 2 session. I'm Martin Kellogg from the New Jersey Institute of Tech, and I will be the session chair today. Our first speaker is Nikolai from the University of Copenhagen. Nikolai, the time is yours. as he comes up. Our next speaker is Zach Kincaid from Princeton. The time is yours.
Okay. All right, there we go. Okay, so this is joint work with my brilliant former student, Xiaowei Zhu. I'm going to start this talk by taking the position that we should be able to understand how changing a program is going to affect our analyses. So this is important to software developers who are constantly changing their code and need to understand, for instance, how a change is going to impact a list of warnings that they get from a static analyzer. It's also important for program analysis designers because we incorporate transformations in our tools, and we want to understand whether a transformation is going to make an analysis better or worse. But many analyses fail to meet reasonable expectations in these regards. So let's take as an example this program. Suppose that we analyze this program using showing a polyhedral analysis, and we find that I must lie in the interval between 1 and 5. And then we insert an extra variable j that accumulates the sum of all the values that I takes, and then we analyze it again using polyhedral analysis. So our expectation is because I haven't changed the computation of I at all, I should still be able to prove the same interval that I had before. But as observed by Magnot and Legun, in fact, just by inserting this j variable, I can no longer prove the lower bound on I. Another example, let's take this little nested for loop, and we're going to analyze it with, say, ultimate atomizer and prove that it terminates. And then we're going to replace this symbolic constant n with a concrete constant, 4096. We'll analyze it again, and our expectation is that, of course, we should be able to prove termination of the program on the right, because to prove termination of the program on the left, we must have proved termination for all values of n. Certainly, we can prove it for 4096. But unfortunately, ultimate atomizer is going to time out after 15 minutes. So these are perhaps toy examples, but it's a real phenomenon. So for instance, in this experience report on the commercial static analyzer Coverity, there's a whole section about the frustrations users have with unstable error reports and the lengths that they go through to avoid them. So they disallow certain analysis techniques that lead to more unstable reports. There's also a slew of other reports of unstable behavior and counterintuitive results in program verification and static analysis, which is nicely summarized by this quote by Leno and Moskal, that tools can understand our programs, but we cannot understand our tools. All right, so this work takes a step towards fixing this problem. So I'm going to answer two questions in this talk. First, what is robustness? So I'm going to give a general language for talking about robustness properties and criteria by which we can understand programs satisfying these properties. And then in the second part, I'll talk about how we can achieve robustness, how we can design analyses that are robust with respect to these criteria. So the overall goal is to provide qualitative guarantees about how we can expect program analyses to react when we change an input program. All right. So informally, we say that a program analysis is robust if it preserves relationships between programs. So this isn't really just one thing, it's a class of properties, because there's lots of different relationships or transformations we want to be able to understand. There's a great number of different robustness properties we might be interested in. So it's really a family of correctness criteria that is indexed by the class of relationships we want to preserve. And our goal is to develop sort of an abstract theory of robustness that doesn't commit to a particular class of relationships or a type of analysis, but allows us to talk about robustness in a more abstract setting. So you can think of this as trying to do for robustness what the theory of abstract interpretation does for soundness. So just a general mathematical language for talking about these things in the abstract. I'm going to start by using a concrete example. So intuitively, program analyses shouldn't depend on the names of variables. So let's suppose that we have an analysis A that maps programs to transition formulas that over-approximate their dynamics. So this is just a logical formula over unprimed and primed variables that represent the state of a program before and after an execution. And the robustness property that we're after is that if P and Q are two programs that are equivalent modulo some renaming of variables sigma, then the same should be true for the two transition formulas assigned to P and Q by the analysis A. All right, so let's graduate from sets to categories. So we're going to define a category of programs wherein the objects are programs, and the arrows are exactly these equivalence modulo renaming relationships. And we'll define a similar kind of structure for transition formulas. Object of transition formulas, arrows are entailments modulo this renaming, taking care to rename prime variables appropriately. So the idea that A should be invariant under renaming of variables should imply that we can lift A from a set that maps programs to transition formulas to a functor that maps this category of programs to the category of transition formulas. So every arrow between two programs P and Q should correspond to an arrow between the transition formulas A of P and A of Q. But this isn't quite what we want. Not only do we have this correspondence between arrows, in some sense they're the same arrow, right? They should correspond to exactly the same substitution. So to encode this, we're going to add another category, a category of finite sets and bijections. And we're going to equip programs and transition formulas with faithful functors into this category. So intuitively, for each of these arrows, we're going to forget about programs and transition formulas and project onto just the underlying substitution. And then the statement that A is invariant under renaming is exactly the statement that this diagram commutes. So for every arrow between two programs, there's a corresponding arrow between transition formulas. And moreover, they correspond to exactly the same variable renaming. All right. So now we can talk about this language of robustness. The basic structure of interest is a concrete category, which is a category C equipped with a faithful functor into a base category B, which we think of as the class of relationships or transformations of interest. And then the fundamental map of interest is a concrete functor. So a concrete functor between two concrete categories is a functor between two concrete categories over the same base that commutes with projection. So every C arrow has a corresponding R arrow that both project onto the same B arrow. And now we can take this like very abstract view that a robust analysis is just a concrete functor. So it's an analysis that preserves transformations, but we're using this highly abstract mathematical language. We already have a nice abstract mathematical language for talking about program analysis. It's order theory. It's the theory of abstract interpretation. So let's compare with that. So we don't lose the ordinary order theoretic vocabulary of abstract interpretation when we move to concrete categories. every concrete category can be equipped with an order relation, which is defined by the set of arrows that project onto identity functions. So this always defines an order, and it allows us to recover the usual approximation order that we expect in abstract interpretation. So in the paper, we redevelop some of the theory of abstract interpretation in this more general language of concrete categories. So we can still do a lot of the things we expect to do in abstract interpretation. The thing that we gain is the ability to talk about approximation modulo transformations. So if we think of our base category B as a set of transformations of interest, then arrows in our concrete category correspond to approximation modulo some transformation. So this could be a renaming of variables, it could be a linear transformation, it could be a control flow transformation, this sort of thing. All right, so the next question is, can we actually design robust analyses? So in fact, there are robust analyses, but we have to be careful about what we mean by that. Robustness is not one thing, it's many things. And so this depends on the class of relationships we want to preserve. But something we notice with this sort of profile of robustness properties of various classic abstract interpretations is that there's a tension between precision and robustness. As we get to more powerful analyses capable of proving more things about programs, these analyses tend to be less robust. And the reason for this is that a lot of the basic building blocks of program analysis, like widening and Craig interpolation, guess and check loops using LLMs, these are all sort of sensitive to representations that make them have poor robustness properties. So if you want to build a robust program analysis, you sort of have to take all of these nice tools off the table. So there's a question of whether we can actually design analyses that are precise like these analyses, but also have better robustness properties. So over the last few years, my group has developed a number of techniques that have shown that it is possible to design monotone program analyses that are competitive with state-of-the-art abstract interpreters and software model checkers. And they all follow the same basic recipe. So we'll take some theory paper that shows that some property of a sub-Turing model of computation is computable. And we lift that to a program analysis using the pattern that we first take our loop, we abstract it in this sub-Turing model of computation, we analyze the model, and then we translate the results back into an over-approximate analysis of the input program. So these are all intuitively instances of the same recipe. In this paper, we show that they are actually formally instances of the same recipe. So there is a category theoretic explanation of all of these analyses, wherein we say, we imagine that we have a concrete functor that maps D to R, where we think of D as being a sub-Turing model of computation. Then we can lift that functor from D to some larger category C, provided C has best abstractions in D. So this is really like the technical meat of all these papers, is proving this like best abstraction result. But we have this, the takeaway here is that we have this like very general recipe for showing that if you have a sound and robust analysis that's just defined on D, we can always lift it to C. So the content of this is number one, we sort of don't need these bespoke correctness proofs for all of these papers anymore. They're just instances of this one general recipe. But maybe even more exciting is that the conclusion of this theorem is stronger. So not only do we prove that these analyses are monotone, this theorem shows that these analyses are robust with respect to linear transformations, which is a much stronger result. All right, the last thing I want to talk about is, I sort of the end-to-end story here. So all of these analyses that I had on the previous slide were loop analyses. They apply to a single loop. And the way that we apply these to real programs is using the framework of algebraic program analysis. So the setup is that we take our control flow graph, we compute a regular expression that recognizes a set of paths of interest, and then we interpret that expression as a transition formula that over-approximates all the paths that are recognized by that expression. And the way we do this is by reinterpreting all of the regular expression operations as corresponding operations on transition formulas. So the connection is that you can think of these robust loop analyses that I was talking about earlier as just different implementations of the star operator. So this raises the question of, in what sense is this entire pipeline robust? What kind of transformations can we do to whole programs, given that all of our operations are robust? What's the end-to-end story? So the bridge here is that this strategy that we have for lifting concrete functors also allows us to transport natural transformations. But the concrete payoff of this is that we have a general way of proving that these iteration operators satisfy certain algebraic laws. And then using these algebraic laws, along with the robustness properties of the individual operators of the analysis, we can show that algebraic program analysis is robust with respect to a class of loop-preserving stuttering simulations, which I don't have time to get into, but I will give you a couple of examples. So if we take a loop and we unroll it some number of iterations, or we split it into a couple of phases, these are transformations that are guaranteed to make my analysis more robust or more precise. All right, so summing up, I think predictability of program analyses is a really important and understudied topic.
Fire alarm. Yep. Sorry, Zach.
An emergency has been reported in this building. Please cease operations and leave the building utilizing the nearest exit or fire exit stairway. Do not use elevators. Repeat, do not use elevators.
Here, give me that mark.
In a moment. I will, actually. Let's you good? Okay. All right, apparently a false alarm. Apologies to everybody for this. Let's all filter back in, and then we will let Zach take questions.
Good?
Really cool work. Fantastic talk. Thank you so much. I was curious about the relationship between incremental algebraic program analyses and robust algebraic program analyses. Could you just say more about that Venn diagram?
Yeah, so I think robustness is a nice property to have for incremental analyses as well. In that, I think Evan did some work on incremental analysis in a non-algebraic setting and encountered issues where if you restart an analysis versus doing it incrementally, you end up with different results and like how to overcome those kinds of problems. Robustness, I think, helps you a lot there because you can actually guarantee that you're going to, like, it's deterministic. Yeah. It's invariant under a bunch of nice transformations. So yeah, I think that there's a good case for why you want both incremental and robust analyses, but I don't think that they interact in the sense that incremental analyses make it easier to be robust, or robust analyses make it easier to be incremental. But I think it's important to have both those properties. And the algebraic framework allows you to do both, which is a nice property.
Hi, how's it? Great talk again. So you mentioned towards the end about the preserving across different program transformations, you can increase your precision of analyses. And I'm wondering if sort of the compositional nature of that is if I go through a compiler pipeline, I do a bunch of different transforms, ideally maintaining equivalence through all of those. And at different phases, I can get different precision of some sort of static analysis. And I'm wondering is, as you go through and do this, should any results at one stage, just going from program A to B, apply all the way through the pipeline? Is this compositional, or is there like a gotcha if I chain a bunch of this sort of analysis together?
So the setup is that you transform, reanalyze, and the question is, do you, what's the gotcha that you're worried about?
I'm hoping you can tell me.
So if you can prove that your analysis is robust with respect to the transformation that you're talking about, then maybe that's an indication that you don't need to rerun the analysis from scratch. Maybe you don't need to rerun the analysis at all. So maybe there's a performance story there. But if the transformations are, say, precision improving, you wouldn't want to do that. Maybe this is an argument for why you should wait until the very end to do your analysis rather than doing it at every step. Yeah, that's an interesting question.
Thank you.
Hi. Thanks. Very nice. I have a question about one of your diagrams. I guess the one where you first abstract to a sub-Turing model and then you analyze that. Uh-huh. And you said that that's always robust. I'm curious if it may be the case that the abstraction is not robust and then you lose robustness because of the abstraction.
Yeah, so there's more to the story. You have to prove that this is actually a best abstraction. So you can't just take any old model. It has to be the best model in some sense. So the best model is it's kind of like a Galois connection. So this weak left adjoint is really saying not only is it an abstraction, it's an abstraction that satisfies a universal property. And it's that universal property plus robustness of the analysis on D that gives you robustness of the analysis.
Cool. And I guess a follow-up question. Have you thought about how that might change if you have some kind of abstraction refinement, like a Seeger loop going on?
I haven't thought about abstraction refinement. Abstraction refinement is one of those things that's really hard to make robust, particularly because we often do abstraction refinement by sort of guessing like a separator between our reachable states and our error states, and that guess is often dictated by a SMT solver, and if you have a different naming of variables, you can get different models or different unsat cores and end up with a lack of robustness. So that's a good question, how you could do refinement with this. But Maybe another answer to this question is this best abstraction result is really saying that there's no way to refine this abstraction in some sense. At least if this is your set of abstractions, this is the best one you could possibly do. So like this is something that, for instance, predicate abstraction, it doesn't have, you don't have a best predicate abstraction unless you have a finite state program. But so we're working with models where you can really get like best abstractions.
Okay, cool. Thanks.
Cheers.
Let's thank the speaker again. Thank you all for your patience through the fire alarm. Our last speaker in this session is Laura from Cornell. And Laura, the time is yours once you're set up.
Hello? Okay, hi everyone. I'm Laura Zielinski. I'm a PhD student at Cornell, and I'll be presenting Synthesizing Backward Error Bounds Backward, which offers a new method for automating a type of floating point error analysis. And this is work done with my advisor, Justin Shu. Now, I'm sure we've all at some point experienced the negative effects of numerical error. It's always something you have to consider when you perform any kind of machine computation. For example, consider computing 1 divided by 3 on your calculator. You know the answer should be an infinite sequence of 3's, but of course it's going to get truncated somewhere. And what about sine of 1 radian? Now you don't even know what the true answer should be. And here's a classic. 0.1 is not representable in binary, so computing 0.1 plus 0.2 is often not going to give you 0.3. And when you pass in these slightly inaccurate outputs as inputs to other computations, the error can compound. Now, I could tell you about the missile that failed to launch or the stock index that lost half its value, but for a really powerful visual of the effects of numerical error, here is the phenomenon of the far lands, which happens when you go really far off the map in Minecraft and the random terrain generator overflows. So the field of numerical analysis aims to avoid these kinds of catastrophes by designing good algorithms that give you accurate results. There are basically 2 definitions of what it means to be numerically stable. If your program satisfies one or both of these, you can be confident that your algorithm is well designed. So the first definition is called forward stability, and it's very intuitive. It means that your computed result is always pretty close to the true answer. But there is a second notion called backward stability, and that's what we're focusing on today. This says that your computed answer for an input is the true answer for a slightly different nearby input. Now, even though it's a little less intuitive, backward stability is widely used to mean stable in numerical analysis, and it has some really nice properties. However, backward stability, up until recently, has almost never been considered as a target for formal verification. So in this paper, we address this gap and provide an automated method for proving backward stability for numerical programs using some tools from PL. Now, I'll give a more exact definition of backward stability and try to convince you why you should care about it. So let's say you pass in an input to a numerical program and get some computed result. It's not going to be exactly the true result, which is over here somewhere. And that difference you call the forward error. But if the program is backward stable, then there exists another input that, if you passed into the exact function, maps to the computed result. And if such an input exists, the distance is called the backward error. So the reason that we care about backward stability is that small forward error is not always achievable. For example, consider the floor function. If you have a tiny error in your input, you can get an answer that's off by a whole number. And it's not the implementation's fault. So even the best program that uses floor can give you a terrible answer. However, if your program is backward stable, you know that your implementation exactly solves almost the right problem. So the output error comes from the problem being hard, not your code being bad. So backward stability is a trustworthy measure of how well your program is implemented and that's why it's often preferred. So backward error analysis is usually done by hand, but the closest prior work done in the space of automated backward error analysis is called BEAN, which was presented at PLDI last year. It's a type system that only allows backward stable programs to type check in the language. And the type checker will actually give you a verified bound on the backward error. However, and I'll get more into this in the next slide, there are many backward stable programs that BEAN incorrectly rejects because they're not yet handled by the type system. So BEAN always gives you a sound result, but there are limitations on the programs it can analyze. The first is that, except in a special case, you cannot reuse variables. So the simplest example is a program implementing ax plus x for inputs a and x. It's incorrectly rejected even though it's backward stable. The reason is that when you use an input in multiple computations, you have to reconcile all of them with a single nearby input, which is sometimes impossible or requires a lot of care in the proof. So BEAN just outright rejects programs like this. But obviously, there are lots of important stable programs that reuse variables, so these are what we target in our analysis. Second, BEAN only allows operations that satisfy its definition of composable backward stability. It is unfortunately too strong to admit square root, which along with addition, subtraction, multiplication, and division is considered by IEEE a primitive floating point operation. So we remedy this in our work as well. So inspired by these limitations, in this paper we offer the following contributions. First, in order to perform any kind of scalable static analysis, we developed a new definition of composable backward stability such that when all subprograms satisfy this definition, we can conclude backward stability for a larger program composed of them. And it's the first definition to cover all 5 primitive operations as well as other correctly rounded ones. Second, we developed a category which serves as a formal framework for constructing backward stability proofs. And we claim that it's easier to prove a program backward stable in this framework than by hand. This is because the category does the heavy lifting of constructing and composing your backward stability proofs. To demonstrate this claim, we implemented a search algorithm through a syntactic version of the category, which attempts to construct a proof that the given program is backward stable and determine what its backward error is. It is a search rather than a type system to accommodate a wider variety of programs than previously possible, some of which have complex or multiple choices of analyses. So in our evaluation, we show that this tool, which we call Eggshell, provides the first automated backward error analysis for a class of programs, which broadly speaking includes programs that use square root and that reuse variables. Okay, so first I'll talk about the new definition that is a backbone of our whole analysis. So again, this time in symbols, here is a standard definition of backward stability as developed in the 1950s. So a program P, which implements a real function f with input x, is alpha backward stable for some non-negative alpha if there exists a nearby input x tilde such that f applied to x tilde is the computed result. And the distance between x and x tilde is bounded by alpha, so alpha is called the backward error bound. And we require that alpha is of the order of machine epsilon, which is a tiny constant that depends on your machine. Now, this definition is what numerical analysts have been using for 70 years, but it poses a significant problem for static analysis, which is that if you have 2 arbitrary programs, P and Q, and you know they both satisfy this definition, there is no way to prove generally that their composition, so running P and then Q on its outputs, is backward stable. And that makes it really difficult to perform a scalable static analysis because local stability does not guarantee global stability. So we developed a new, stronger definition that does have this property. So the differences here are highlighted. So now we say a program P is alpha beta stable if for all y at distance bounded by beta from the computed result, there exists an x tilde that maps to y under the exact function. So before, we only cared about mapping to the computed value p of x, but now we need to be able to map to any value y near p of x. And this definition is very nice. So first of all, it composes. So if p and q are this version of stable, then we can run p and then q and guarantee that it's also stable. And second, it is a generalization of the standard definition. So if a program is alpha beta stable, then it's very easy to show that it is also alpha 0 stable, which is exactly equivalent to being alpha stable, which was the standard definition. And the punchline is that it's actually very flexible, so it's easy for operations to satisfy this new definition. The Bean paper offered the first composable definition, but it was too strong to capture some operations, and this excluded programs that use them from the analysis. So ours is the first one to capture all 5 primitive floating point operations, and in our paper, we prove that it handles other operations such as correctly rounded logarithm. So this definition is what we're going to use for the rest of our paper when we say backward stable. Okay, next we embed this definition into a framework for constructing backward stability proofs. We chose to develop a category which we call shell, and it stands for shifted error lenses. So a crash course, a category basically consists of a collection of objects, and for every pair of objects, a collection of morphisms that go between them from a source to a target object. And given 2 morphisms, their composition is also a morphism. For example, you're probably already familiar with the category set, where objects are sets and morphisms are functions. So for our category, we say our objects are floating point variables, and the morphisms are stable programs. So a morphism source object represents the program's input variables, and the target object represents its outputs. Now, there are a bunch of benefits of using a category for our framework. First of all, since we define generally how morphisms compose, we can just work within this abstract mathematical structure, not worry about the actual low-level details of error analysis, and in the end, prove backward stability for free. Second, we enrich the objects to encode information about the relationships between intermediate variables in a program. And this is what allows us to handle more complex analyses. These relationships constrain what operations you're allowed to apply while maintaining stability, since, as I said before, not every program is backward stable. So to use this framework, you just have to try to conform your target program by composing together a small set of morphisms. And this will guarantee that your program is backward stable. We also encode the backward error bound into the objects, and if you want, you can extract the proof from the final morphism. And I'll show you an example right now of how this works. So for a very simple example, let's say we want to prove that a particular program implementing ax squared plus x for inputs a and x is backward stable. There are a few different implementations, but I have a particular one in mind. We know a small set of morphisms in the category shell, one for each floating point operation, and a few others that just rearrange the context. And we want to compose them to form our target program. So we start off with an object that represents our input variables x and a. The first computation is a multiplication of a and x, so we apply the morphism that corresponds to this. This morphism returns the x variable for reuse. Now the star means that these 2 intermediate terms are related. Intuitively, it says that ax has a factor of x in it. If you're interested in category theory, I highly recommend you read the details in the paper, as we define the star as a generalization of the tensor product. And now we multiply our terms again, so the star now tells us that the ax squared term has 2 factors of x. And now we apply one of our morphisms, which doesn't actually do any computation. It just changes the relationships between variables and the underlying backward stability proof, but we don't have to worry about that. And it puts the context in the right shape to apply this addition operator, so the cross expresses a different relationship between those terms. So now we've formed our target program by composing a few building block morphisms. At this point, we're able to conclude that the program corresponds exactly to a morphism in shell. And since morphisms represent backward stable programs, so is our input program. I omitted it for most of the objects, but if you look closely at the source objects, you can find the static backward error bounds on our inputs x and a. And if we unpack the morphism, we can get out the actual proof of backward stability. In our paper, we have more complicated examples which better illustrate how our approach simplifies stability proofs, such as for the Cholesky decomposition. Okay, for a little more detail on how this works, a morphism in shell contains the following information. So let's say we have a morphism, so a backward stable program between 2 objects x and y, where x represents the inputs and y represents the output. So the morphism contains the program as well as the function it's modeling, but also a map going from y back to x, which we call the backward map. And it provides some important information. It gives the backward stability witness, so the nearby input, for not only the current program, but also for future completions of the program. And that is what allows the morphisms to compose their proofs. And I'll mention that these morphisms are an instance of lenses from functional programming, which generally have forward and backward maps subject to some lens laws. So the algorithm of our automated analysis basically does what we just did in the example. We define a syntactic subcategory, so string representations of some of our objects and morphisms, and used egglog to search over all the potential morphisms that could form the target program. We used egglog because it offers logic programming, which we use to match on the target program and apply potential morphisms, as well as equality saturation, which we use to rewrite isomorphic context. If the search is successful, then it returns the backward error bounds that it found, because sometimes there are different proofs of stability with different bounds. And this is an example of running our tool. So diving a little more into how this works, we define syntactically a shell object, which we call a context, and then we define a relation, arrow, on two contexts, which means there is a morphism between the underlying objects. A context also encodes the desired numerical expression that you want to prove stable. So each datalog style rule is able to match on your current context, look at the top level operation, and apply a morphism that matches that operation. For example, if you pass in this program, eggshell will match on the top level multiplication and apply these two matching rules, giving us two new contexts, which it repeats the process on. And each rule updates the backward error bounds. So the difference between these two rules is which subexpression is getting the error from the computation. We do it again, and in the end, we check the relation and look for contexts that match a set of input variables. So here, we found two such contexts, and each one corresponds to a morphism to the target program, proving it's stable. So we returned two sets of backward error bounds. And you'll notice we did the search backward from the target to the source, so the paper title is a little reference to that. So we implemented a few dozen of these rules, and that enables Eggshell to prove backward stability for a wide range of new programs that no other static analyzer was able to handle. And generally, these are stable programs that use the square root operator and reuse variables. Our implementation often returns many different proofs of backward stability, each with a different set of error bounds, which can sometimes be useful. And there doesn't appear to be a standard benchmark yet for automated backward error analysis, but please see our paper for example programs. Thank you for listening, and I'm happy to take questions.
Questions from the audience?
Very nice talk, Laura. Actually, the fact that you overcame the duplication of variables is a big step forward. 2 talks earlier in another session, I heard the authors discuss Strassen-like matrix multiplication, which is not backward stable as far as I have read. So could that be a benchmark? Strassen matrix multiplication is a recursive matrix multiplication. It's supposed to be faster, but it's known to be not backward stable. I'm not an expert, but I was trying to see whether that could be a nice benchmark for your tool. Yeah, we can talk offline if the question is not clear.
I'm not sure, because
Yeah.
it's not backward stable,
So,
I don't know.
Yeah, okay, we could maybe try it in your tool.
Yeah, sure,
Thank you.
I'd have to look at the program. Thank you.
We'll try.
This is really great work. Thanks very much. So I wondered about programs that have conditionals in them. So this is a kind of classic problem in numerical modeling where you have some sort of inequality over something in floating point and it leads to stability issues. So do you have a story about how to think about these kind of co-product-like branching kind of structures?
Sure, yeah, so conditionals are famously an example of another ill-conditioned operation, but I believe they actually are backward stable because the previous tool Bean was able to have conditionals. So this is definitely future work. We need to define co-products in our category, and I think it could be doable though.
Yeah. Okay,
Yeah, thanks.
Cool, thanks.
Thanks for the really great talk. You mentioned that Bean has a compositional definition, but that yours is different and maybe is what allows you to permit square root. What is the difference between
Sure,
their
so if you remember our definition, it said something like for all y surrounding. For all y surrounding the output, you need to be able to hit it. So Bean said for all y in the output space, you need to be able to hit it. And also, they had a different inequality for proving the backward error bound that was a bit too strong. Yeah.
Thank you.
If there are no more questions, let's thank the speaker again. And that concludes our session for today. Thank you all for coming.
Thanks, Martin. You did a great job.
I did nothing. It was really easy.
All right, let's get started. I am Chen Chuan from the University at Buffalo. So this is the session for verification and proof reasoning. If you are in the wrong session, I mean, you should still stay. But here is our first talk. Samuel is our first speaker, and he's also on the academic job market this year. So if you are hiring, please talk to Samuel offline. And he will be giving a talk about heterogeneous dynamic logic.
Right, thank you very much. Do we have the slides? All right, thank you. So I will be talking about the verification of heterogeneous systems today. My name is Samuel. This was joint work together with Matthias Ulbrich, Andre Platzer, and Bernhard Beckert. We're all at KIT in Karlsruhe. And so when I talk to people about this in the last days, usually the first question was, well, what's a heterogeneous system? So let me maybe give us some examples for what the kind of systems that we're interested in. So for example, in this work, we have a case study where we have a piece of software, a Java software, that's controlling the acceleration of a car. And so then basically you have two very different computational worlds. On the one hand, you have Java with objects and heap and so on and so forth. And on the other side, you have differential equations, a model of your physical system. And we have good tools to reason about them individually, but now we want to reason about their combination. In some of my previous work, I looked into the verification of neural networks in cyber-physical systems. Again, the question is kind of how can we combine these two very different computational worlds? A former colleague of mine verified hybrid systems where you have a quantum circuit and a Java software that is measuring this quantum circuit. Again, two very different computational worlds. And as I said, we have good tools for these worlds individually, but then the question is how can we combine these tools? And my feeling is that often so far the solution is kind of that for any combination, we kind of come up with a custom solution. And so we kind of end up with n to the power of 2 custom solution if we're combining 2 systems, and even more when we are combining more systems. So the question is kind of, can we come up with something more rigorous? Can we come up with an approach for the combination of program logics? And so for the purposes of this work, when I'm talking about program logics, we will be talking about dynamic logics. However, I want to emphasize that obviously, like if you squint, maybe you can squeeze some program logics into this formalism, even if they are not strictly dynamic logics. Now, just to get everybody on the same page, dynamic logics, you can think of them as a modal logic, where you have a modality, and inside this modality, you have a program. And so then we can write a formula like box alpha psi, where we're saying for all runs of alpha, afterwards, psi has to be satisfied. The nice thing about modal logic is there's also a dual operator, the diamond operator, which lets us state that for some run afterwards, psi has to be satisfied. And if you're more familiar with things like a Hoare calculus, for example, then we can also translate the classical precondition, postcondition paradigm into dynamic logics by basically writing an implication, and then phi is our precondition and psi is our postcondition. Another nice thing about dynamic logics is that they allow us to compose these different modalities, so we can write down a whole range of different properties where we reason about the same program multiple times or different programs and so on and so forth. And so the contribution of this work is that we're introducing heterogeneous dynamic logic, which is meant to allow us to combine different dynamic logics. And so to this end, we rephrase individual dynamic logics, and these could reason about Java or about differential equations or about an entirely different program paradigm. We reframe these dynamic logics as dynamic theories, and you can think of them as puzzle pieces. And with these puzzle pieces, we can do 2 things. First, we can lift them, which basically means we take an existing dynamic theory and we extend the functionality of its programming language with additional features and calculus rules to handle these additional features. And we can do combination, which basically takes 2 dynamic theories and forms them into a new dynamic theory, which can reason about the combination of these individual programming languages. Now, this whole system is meant to be BYOP, which stands for bring your own proof. And so the idea is basically that if we have a combined system, then we want to be able to decompose this into proof obligations for the individual systems where we already have proof infrastructure in place. Now, the proof calculus rules that I'm going to talk about today, we've all formalized them in Isabelle HOL. And also, I will later be talking about relative completeness, because we also have some results on the power of this calculus. But before we get into these details, maybe first of all, what is a dynamic theory? And I want to motivate this with the example of first-order dynamic logic, which is one of the very basic dynamic logics where basically you just have integers or at least if you instantiate it with integers, you just have integers. And so here we have a loop which runs non-deterministically and which updates x to x plus 1 for an arbitrary number of iterations. And so ideally what we would want is we would want to abstract all of this away, right? Ideally we would want a kind of a paradigm that allows us to have black boxes here for the programs and black boxes for the predicates, and somehow we could still kind of then combine things. However, if we want to combine things, we probably also want to pass values between these different worlds, right? So kind of we want to keep variables. Without variables, this exists. This is propositional dynamic logic. However, we also have variables. And so then we can basically define the signature of a dynamic theory through its variables, its atoms, and its programs. And with that in place, we can then also define the syntax of dynamic theory formulas exactly in the way you would expect, right? So we have a modality for programs and a quantifier for variables and so on and so forth. And so now to give meaning to this, we must determine the meaning of variables, atoms, and programs. So let's start with variables. For variables, the idea is basically we define a universe and the state space. And then we have a variable evaluation function, which takes a state and a variable and tells us which value in the universe this variable has. Now, unfortunately, we can't take any arbitrary combination of these three constructions. We must consider some notions of well-formedness for these dynamic theories to work out the way we want to. In particular, for example, for variables, we require something that we call state independence. And the idea is that if we have two states in our state space, which evaluate variables to these orange and these blue values, then we must be able to take a subset of these variables and construct a new state which basically combines these two individual states along the lines of this variable set. And this must again be in the state set. So this is kind of an assumption that we have to make about how our state space looks. And now I'm going to introduce how we evaluate atoms and programs. And again, there's going to be some side conditions. So for atoms, the idea is basically that for any atom, we have a function that tells us which set of states this atom is satisfied. And for programs, the idea is that for any program, we have a state transition relation which tells us which state transitions are possible. I mean, this is rather straightforward. What's maybe important to note here is for each of these, we also have a definition of free variables, which tells us which variables influence the evaluation of the program. And here again, we're going to have some side conditions, which basically make sure that these free variables correctly represent the actual free variables that influence atom evaluation or program evaluation. And we must also assume that these free variable sets are finite. Additionally, we must assume that the program evaluation is extensional with respect to variable evaluation. Now, I don't have time to go into all the details of this, but again, this is formalized in Isabelle, and the idea here is that this is a locale. And so basically, whenever you can, if you know Isabelle, you can then basically instantiate these locales to get your concrete dynamic logic. With this defined, we can then define the semantics of formulas, and it's defined in basically the way you would expect. I just briefly want to highlight the box modality again. So box PF basically means for all state transitions induced by our program evaluation function, afterwards the formula must be satisfied. With semantics in place, we can start reasoning about these formulas. And so we want to derive proof rules. There's just one hurdle left, which is that usually when you're deriving proof rules, especially in dynamic logic, we kind of want to know which variables are free and bound in a program or in a formula. Now, we already talked a little bit about free variables. However, the problem here is that we can't really give you a general syntactic analysis for this, because obviously this very much depends on the dynamic theory that you're precisely looking at. So our solution is that there exist actually semantic definitions for free and bound variables. And so we assume these in our calculus, and whatever superset you can come up with, you can then use to apply your calculus rules in practice. And then we can indeed derive some calculus rules. I just want to highlight here Barkhan's axiom, which actually can be proven for all dynamic theories, and which basically states that under certain conditions we can swap a box modality and an all quantifier, which is sometimes very useful. Now, if you're more interested in, for example, clean algebra with tests, we also have an axiom for you. So there is actually an axiom which allows you to basically rewrite modalities based on equalities, program equalities that you derived via clean algebra with tests. So we can also connect to that. For some concrete instantiations of dynamic theories, propositional dynamic logic can be instantiated as a dynamic theory. Differential dynamic logic, which lets you reason about cyberphysical systems, can also be instantiated as a dynamic theory. And indeed, there is an Isabelle formalization of this in the archive of formal proofs. And we've formally shown that this instantiates our dynamic theory. And also Java dynamic logic, which lets you reason about Java programs, can be instantiated as a dynamic theory. What's a much simpler dynamic theory is this dynamic theory here, where basically in the modality we can only have assignments with a single semi-ring expression. So in here, this is going to be a very simple example that I'll come back to later. In this very simple programming language, all you have is kind of one assignment of a variable to some semi-ring expression. So this could be integers, real values, something like that. At this point, you might start wondering, well, you only really derived 4 axioms for these dynamic theories, right? Why is this worth it? What's the use of defining these dynamic theories? And so here it's important to remember that this is really only the first piece to the puzzle. Because once we have this, we can now start lifting these dynamic theories. So in particular, for example, we have a Havoc dynamic lift, which extends the programming language by an additional primitive that arbitrarily sets and initializes a variable. And what we can then do is basically for any dynamic theory, we prove that if you lift your dynamic theory with this additional feature, we have calculus rules to resolve this additional feature. And we have a Havoc reduction rule, this HR rule here. And so this rule basically tells us that if we were able to derive something in our original dynamic theory, then we can also derive it in our Havoc lifted dynamic theory. This allows us to basically reuse the proof infrastructure we already have for the original dynamic theory and reuse it in our lifted dynamic theory. Now, Havoc lifting is still a very, very simple kind of lifting. However, we also have a regular lift, which then basically gives you the regular closure over the programs that you had beforehand. So now you have sequential composition, non-deterministic choice, loops, and also checks, which allow you to check with respect to some first-order formula whether something holds or not. Again, we also derive calculus rules for this. In particular, for example, an induction scheme, and again, a reduction rule that allows you to reuse your existing proof infrastructure for the underlying dynamic theory. Now, so far, the only assumption we've had here is that what we're putting in is a dynamic theory. If you allow us to have some more assumptions, and more precisely, if you allow us to have an assumption which states something like, there exists something like integers in my dynamic theory, then we can also give you a loop convergence rule, which basically allows you to prove things like loop termination. Now, going back to the semi-ring dynamic logic that I was presenting earlier, in the simple semi-ring dynamic logic, all we can write is these modalities with a single variable assigned to some semi-ring term. If we now lift this dynamic logic with this dynamic theory with Havoc and with this regular lifting, suddenly we can write formulas like this one, where the program already looks a lot more interesting, right? So now we have loops, and basically what's happening here is that we're having a non-deterministic loop where in every iteration we add some positive number on top of the x we already have. And even better, if we now wanted to prove this, we could use the calculus rules that we derived so far, together with the fact that in the original dynamic theory, the formula at the top is valid. So basically, the validity of the formula in the original dynamic theory, we could reuse for our proof of the formula at the bottom. So much for lifting. But what we really wanted to get to, actually, was combination, right? So how does combination work? Well, the idea is basically, if we have 2 dynamic theories, we construct a new dynamic theory that combines the 2 original dynamic theories. The way this works is that, first of all, for variables and for programs, we take the disjoint union. So we assume that the programs are disjoint. I mean, you can label them somehow so that this works out. And then for the universe, we also just take the union of these 2 universes. Now, the question, obviously, is how the semantics look, right? And so here, the idea is basically that for the state space, we take the cross product of the 2 state spaces. So now our state has 2 components, one component for dynamic theory 0, one component for dynamic theory 1. And then if we want to evaluate a variable, for example, we basically just evaluated it with respect to the corresponding component of our state space. For atoms, this also works basically by the component of the state space. However, we also introduce some additional atoms that reason about the combined state space, and these then allow us to basically constrain the kinds of states that we're in. So this would allow you to do something like saying, this real valued variable relates to this integer valued variable in my other world in a certain way. For program evaluation, the idea is then basically that the program evaluation only ever advances the one component of the state space that is corresponding to the corresponding program. And with that, we get a very basic heterogeneous dynamic theory. So we have some additional atoms here for reasoning about the combined state. However, there's still one issue, which is that so far in the modalities, you can only ever have a program from one theory or from the other theory, because all we had was kind of this union, right? However, there's a solution to this, which is lifting. So now basically, if we lift this dynamic theory with the regular closure, suddenly we can reason about any regular program over the two original dynamic theories. We again derive some proof rules for this. In particular, we then have heterogeneous reduction rules, which allow you to basically say if some formula was valid in the original dynamic theory 0 or in the original dynamic theory 1, you can also have it in the combined dynamic theory. And you can also derive something that looks a little bit like a frame rule, where essentially you say if you have some program from dynamic theory 0 and you have a formula from dynamic theory 1 that appears before and after the program, then you can factor that out because the program can't affect it. With this in place, we can now write formulas like this one, where essentially we have in the precondition something from dynamic theory 0, in the postcondition something from dynamic theory 1, and in between a regular program over programs from the individual dynamic theories. So for example, here we first assign x to something, then non-deterministically assign y, have a check that reasons about the combined state space, and then run a differential equation from dynamic theory 1. An obvious question is now, you can state something like this, but can you also prove it, right? And so that leads us right to the question of, can you prove all valid formulas with this calculus, right? The completeness question. In dynamic logic, people are usually more interested in relative completeness, where the idea is basically we assume we have an oracle for modality-free formulas, and then the question becomes, can our calculus basically resolve everything to questions that only reason about the data theory, so to say, the first order theory. And here we have some relative completeness results, which basically state that a relative completeness is preserved under lifting and combination under some reasonable assumptions. I want to state that this is only proven with pen and paper. We also did a small case study that I don't have a lot of time to go into, but basically the idea is we had this Java controller and the cyber-physical system, and then basically we were able to derive one part in Key, one part in Chimera X, and bring these results together to get a system-level guarantee for the heterogeneous system. Right, and with that, I want to conclude. I talked about lifting and combination today. And for future work, we're interested in looking at more case studies, looking at integrating more logics, and also integrating that with neural network verification to reason about AI-based systems. Right, thank you very much.
Questions? If you have a question, you can walk up to that mic and ask. Yes? Or you can use this one.
Yeah, so there's of course some relation here to ordinary theory combination, right? Nelson-Oppen for non-modal logics. The same kind of reasoning about free variables and relationships between them. I'm asking you to speculate a little bit, but do you think there's a way to, one of the great things about Nelson-Oppen is that it can be automated efficiently as well. Do you think that's something that with, future work that this could be useful for, right? Automating this kind of language combination and reasoning about that for verifying programs.
Right, I think we can maybe automate certain fragments of it. I mean, we have to kind of keep in mind that if we look at the general problem, then we already have arbitrary quantifier alternations here, which already, like Nelson-Oppen, would fail even if we don't have modalities, right? But I think, yeah, maybe we can automate certain fragments by doing things like backward predicate computation or something like that. I think there's a possibilities there. Yeah.
So I was wondering. Pardon me. You get a sort of separation in the state spaces, and I was wondering, that obviously is related somehow to separation logic and the separation conjunctions and separation logic, and that obviously raises a pile of possible questions. But the thing I was wondering is, if you have separation logic in one of your dynamic theories, will it play together?
Right. This is something I haven't looked into yet that deeply. I know there is also like separation dynamic logic. So a natural question to ask would be, can we kind of integrate that here? What's important to keep in mind here is the kind of the way we have the separation of state space here is kind of by construction, right? So it's not like that we divide the heap during the proof or something like that. So maybe it's not exactly,
right.
but it's definitely related.
Right.
Yeah.
It isn't quite the same, but it's clearly related.
Yeah. Yeah.
Okay.
All right, let's thank the speaker again. Okay, next up we will have Cass, who will tell us about how to use recursive coalgebras to prove algorithms correct.
All right. Yeah. Can you hear me? Okay. Yeah. So this is joint work with Henning Obert and Thorsten Wissmann. Thorsten is also here. And sort of our setting is structured recursion, which is a discipline of using category theory to analyze and describe the recursive structure, the recursion structure of algorithms. In particular, there's one type, there's a specific instance of structured recursion that allows us to describe divide and conquer algorithms in a modular way. The problem of using this technique is that in total functional programming languages or proof assistants, it's difficult to prove termination of algorithms defined in this way. So our contribution is that we came up with a new notion that gives us a sufficient criterion for proving recursivity of coalgebras. And this has some neat further applications. So it's not only useful for mechanized proof, but also traditional proofs in coalgebra. It dovetails very neatly with intrinsically correct algorithm construction, which I will illustrate during this talk. Then we have a mechanization of our main proof, and we also have an ACTA library for using this technique to write intrinsically correct algorithms. Then in our paper, we have next to the quicksort example, which I will sort of use throughout this talk, we also have applied this technique to intrinsically correct CYK and GCD algorithms. All right, so we begin by dividing and conquering divide and conquer. Namely, a divide and conquer algorithm can be divided into these three steps, right? You divide your input into smaller inputs, then you recursively apply your algorithm, and then you combine them again. And so this smaller thing here is a Chekhov's gun. One of the textbook examples of a divide and conquer algorithm is quicksort. You partition elements of the list around a pivot, then you do that recursively until you reach the empty list, and then you just concatenate the ordered list that you've created. So that's just like an in-order traversal of a binary tree, essentially. And so what we will focus on is the divide step of quicksort, which we call partition. I do want to note that this analysis of quicksort as a coalgebra to algebra, or coalgebra to algebra morphism, is from prior work. What's new is this verification and proving recursivity. All right, I've made a nice little ticks animation which shows how actually this sort of works on an example list. So we start out with this input, and then we pick our pivot. Like in this case, we pivot around the last element of the list, and we sort of partition the elements into the elements that are smaller and the ones that are bigger, and we sort of keep applying this partition function to the newly generated lists until we reach the base cases, which are like leaves of a tree. And the interesting thing to note here is that essentially the call tree of quicksort is a binary search tree, and can actually sort of be reified as this data structure. Okay, now the diagram, first diagram, it looks a bit scary at first, but I want to try to motivate this. The partition step does this, right? I take some list and a pivot, and I'm splitting it up into these sublists to continue iterating on, and then I recursively sort the lists that are smaller and that are bigger, and then I combine them here, and this sort of motivates the abstract definition of a divide and conquer algorithm as a coalgebra to algebra morphism. So for a general algorithm, you would have the division step, which is given by a coalgebra. Then you have a functor which describes the way that you're dividing the input into smaller inputs to recur on. And then the functor also has an action on morphisms, which you apply to the algorithm you're defining recursively, and then an algebra combines the outputs after you return from the recursive call to produce the final result. And yeah, so for our example algorithm of quicksort, the functor that gives the structure is like 1 plus x times a times x. So 1 is like the leaf base case, and this is the case where we're picking out a pivot and lists. And now I'm introducing the notion of a recursive coalgebra. So a recursive coalgebra is precisely such a coalgebra such that we actually can get like a morphism that makes this diagram commute. So essentially this functional equation holds. And this is essentially what we're trying to get to, right? Proving recursivity of a coalgebra, because if we do that, then we can use it to define algorithms. In a language allowing for general recursion, of course, you could just sort of read this as a recursive definition. But since we're in a total functional programming language, this equation might not necessarily have a solution. So we're trying to look at coalgebras for which this equation does have a unique solution. All right. And so this talk is called Intrinsically Correct Algorithms and Recursive Coalgebras, right? So this is the part where intrinsically correct algorithms enter the scene because they are sort of what motivated this new technique for proving recursivity. So by intrinsic proofs, I mean like we're working with data indexed by other data that is like relevant for proving some functional properties of the algorithm that we care about. And it turns out that in all the examples, at least that we study in the paper, but seems to be like a recurring pattern, that often this data that we use for proving these functional properties already suffices to give us a sort of like ranking argument, which we can use for proving recursivity, and that's where we introduce the notion of a well-founded functor. And in the following, we'll do this, show this motivation for an intrinsic correctness proof of quicksort. Here's another sort of brief slide to motivate intrinsic correctness proofs, maybe if you haven't encountered them before. The idea is that the thing on the left-hand side corresponds to like an extrinsic proof. You will have an algorithm that's like maybe in some simply typed language, and then next to that you have a correctness proof. And often like if you have a recursive algorithm, you usually have like some proof by induction that proves the correctness, and so you kind of get this like structural duplication between the definition of algorithms and the proofs of their correctness. And intrinsically correct definitions essentially do both the algorithm and the correctness proof in one go. All right. So yeah, how do we prove or how do we define intrinsically correct versions of quicksort? The thing to note is that, okay, there's two properties that we care about: orderedness, right? The output that we're producing should be ordered, and element preservation. So the output should be a permutation of the input. And sort of the insight that leads us to an intrinsic formulation of this correctness is to say that we can formulate the permutation property as element preservation. Essentially, the input and the output have the same multiset of elements. And then if we index all our data sort of with the multiset of the elements they contain, then what we're looking at is just index preservation. And in the paper, we also use like this index to prove the orderedness, but that's not relevant for the termination aspect, so I'll focus only on the element preservation aspect for now. Okay, so how do we introduce this element indexing? Well, we sort of, we originally had our functor, which was just 1 plus x times a times x. But now we want to be more specific. We want to say if we have some date, like some input x with f, which tells us sort of what the multiset of its elements is, then we either go to send this to 1, and well, 1 like sort of like the single element set that corresponds to like leaf nodes, and this doesn't contain any elements, so it's mapped to the empty multiset. Or in the pivot case, we're combining the like multiset indices of the recursive positions with the pivot to produce the multiset index of that. And the thing to note here is that the index in this product case, the outer index has strictly more elements. So in some sense, it's larger than the indices of like the recursive or functorial positions. And this is what we will use to prove termination. Yeah, so for now, this is only like a sort of an observation, and what we need to do is to formalize it. So what does this exactly mean, right? Like how do we refer to like the recursive positions for some general functor, that kind of stuff. And that's what we do next. And for that, I need to introduce like a bit of notation. So we'll work in some index set W, which has a well-founded ordering on it. The one thing that will come up is the down set, which is like for some element I. The down set of I are all of the elements that are smaller than I. And then if we're looking at families, at W-indexed families in some category C, we introduce like two functors that we can use in this setting. One of them is restriction, which takes like a family that's defined on the whole index at W and restricts it to just the downset of I for some I in W. And then the other projection is just evaluation, right? We have a whole family and we evaluate it at some concrete I in W. And these definitions will now help us express our notion of a well-founded functor. But I'll first begin with the intuition. So the intuition is a well-founded functor is one that where sort of like pointwise the output of that functor is fully determined by inputs at indices that are strictly smaller than the output index. Also, in introducing a bit more notation, we can express this as sort of this functor from C to the W to C to the W is morally equivalent to actually a family of functors for every I in W from the downset of I to C. And this leads us to like our full statement. So a functor is well founded if the composition of like evaluation after application of the functor factors through restriction. So I'm taking like the input family, which is defined on like the whole index at W, and I'm restricting it to be only defined at indices that are smaller than my output I. And then the point is that this should commute, and that expresses sort of that like this is already determined. Like I'm not losing any information by restricting down. Right, and that leads me to the API that we provide. So the way our proof is structured is essentially like you as a user of the library or of this theorem, you have to provide some things, and then we construct some things. So you provide an initially you provide your functor that's just an endo functor on C to the W. Then we restrict it in a sort of canonical way to a family of functors indexed by I from C to the downset, and we get a projection that sort of goes this way. So this family after the restriction to the evaluation at I after F. And like if we look back at our previous definition, right, like we say a functor is well founded if this sort of square is a natural isomorphism. So what you have to do is you have to provide an inverse to this embedding. And maybe this looks a bit abstract for now, but then on the next slide I'll show what this looks like for our running example of quicksort. Here we have a tree functor, like this corresponds to the thing we had earlier on the slide, where I have like a leaf case, right? This is indexed by the empty multiset, and then I have a branch case, and here I'm combining like the multiset index of the left thing and the thing on the right and producing this output node. And so the thing that you as a user now have to provide, right, is this inverse to this projection. So you get a value of txi, and then you have to produce a value of t and this thing. So this is like our canonical definition of this family of x after the restriction has been applied to it. And this is the term, and I'll explain how we sort of arrive at it. And the first thing we do is, right, we obtain a value of this type. So we pattern match on it. Right, and then we're either in the leaf case or in the branch case. And we have an inductive family, right? So pattern matching lets us conclude information about the index by inversion. So in the leaf case, we know we are indexed by the empty multiset, and in the branch case, we know that like this is the shape of the multiset index. And then to construct this function, what we as the user must provide are just proofs that the indices here are smaller than the outer index. But because we've refined the outer index, like we now know that it has this shape. So it's like fairly simple to construct a proof that, you know, like the left multiset is smaller than the one that has a pivot and correspondingly for like the right multiset. So yeah, so that's what this looks like for actually defining an algorithm. Some future work is to express like more algorithms. As I said, we have sorting, quicksort, CYK, and GCD. And to sort of put this to a more extrinsic setting maybe, because we're working a lot with index data, and then also connect to more established notions about well-founded recursion. To conclude, we've introduced like a new way to express a broad class of algorithms in total functional programming languages in a way that modularly we can prove their termination and functional correctness properties. The notable thing is that these two approaches sort of dovetail with in this index setting. Yeah, if you're interested in more applications or corollaries of our main theorem that you can use for other proofs in the setting of coalgebra, please have a look at our paper. That's it. Thank you.
Questions?
Thank you for a great talk and very nice ideas. Just curious about how large this category of the functors, which you have these well-founded functors, how expressive is this class? Does it include all the polynomial functors and so on? And can you say something about adjunctions within these functors?
So actually there is. Like in our paper, we have an adjunction. There's like the category of well-founded functors, and then like our construction that we do, like this canonical way of obtaining a well-founded functor from the original one, is a co-reflection. But like there's not such a big a class of like functors that are like automatically well-founded. Because like if we look at just like a tree functor that, or like the 1 plus a times 1 plus x times a times x, this isn't generally well-founded, right? Like there's no guarantee that this gets smaller. So it's so far in all of our applications, essentially the functor in question has been specific to the algorithm that we looked at. Yeah.
Thank you. Yeah, that's lovely work. So I think my question is somewhat related to that. So in this example, you're using bags, and then you have a well-founded ordering over bags, multi-sets, right? Is there some sense in which this is usually the right kind of structure, like multi-sets are some sort of canonically useful kind of way of doing this kind of proof? Or what are the other examples, I suppose, of things you use for the well-ordering?
Yeah, so for CYK, for example, we use strings because it's like grammars and that's sort of the guardedness there, right? The multisets are sort of the right notion to use in all of the sorting examples. For our GCD application, we just use like natural numbers.
Okay.
Yeah, so it sort of is kind of domain specific.
Yeah, okay. That makes sense. Thanks.
Yeah.
This needs to be a quick question.
Okay, yeah. So this is very nice work. So in your CYK example, like when you construct the fixed point, like can you make that fixed point combinator sort of generally memoizing, so you get the complexity bounds for CYK parsing as well?
I think we don't do this just because I think it would be a hassle to do in Acta. But I guess like you could prove that it's like equivalent, right? Like memoization is like a transformation you can sort of apply to things, and that should be permissible.
Okay, thanks.
Yeah.
Right, let's thank the speaker again. Our next talk will be given by Yonghee, and he will talk about Chris and the power of imagination.
Hello everyone, I'm Yonghee Kim, and today I will present Chris, the power of imagination in hybrid verification. The main motivation for this work is hybrid verification, so let me begin by explaining what that means. Before we get to hybrid verification, let me first recall the standard program logic. Here, each component is verified against a logical specification typically given by pre and post conditions. In separation logic, these specifications also describe ownership of resources. This allows us to reason locally about one component at a time without tracking the whole program state. But there's a limitation, as adequacy theorem gives us a safety guarantee only when every program component has been verified. So I will call this full verification. But there's another approach. Even if we verify only some of the components, we can still get the formal guarantee about the whole program. This guarantee takes the form of contextual refinement between a concrete implementation and an abstract model. It says that the implementation's behavior always refines the abstract models under any identical context. In this picture, we set the context to be an unverified application. And that gives us a formal guarantee relating the source and target side. Concretely, the behavior of the implementation linked with application refines that of the abstract model linked with the same application. And frameworks like CCR, Simularis, and Relog support this kind of reasoning in the style of separation logic. Then we can apply lighter weight methods to the abstract program, things like model checking or testing, and because its state space is much smaller than the implementations, model checking or testing gets a lot more efficient. This is what we call hybrid verification. However, these frameworks share one important limitation. Their specifications are restricted to pre and post conditions. To see why that's the limitation, let me show you a motivating example. On the left side, there's a simple library called cell. There's one private variable, CV, that holds a value, and two functions that update or read it. The set function takes a callback CB as its argument, calls it, and stores the callback's return value in the private variable. Note that these gray box components will not be formally verified. They will be tested or model checked later instead. And the get function just returns the current value. So how do we specify this library using pre and post conditions? Let's see the get function first. Here, cell X is an ownership predicate. It represents exclusive ownership of the cell, indicates that the current value is X. The precondition requires the caller to provide this ownership before calling get, and the postcondition guarantees that get returns the current value, so R equals X, and it gives the ownership back unchanged, and that's cell X again. So together, the pre and post conditions precisely capture the get's behavior. For set, we can write something simple like this. The precondition requires ownership of the cell with some value X, and the post condition gives ownership back, but now with an arbitrary value Y. This captures the set may change the cell, but it loses the information that the new value Y came from the callback. So normally, we would recover that by assuming a parametric pre and post condition for the callback, but the callback stays unverified here, so that assumptions will never be discharged. And with no discharge, there's no formal guarantee follows. To address this limitation, we introduced a new notion of specification, which we call imaginary specification, and a proof system that supports them called CRIS. The key idea of imaginary specification is that they can freely mix program code with separation logic assertions. To see this clearly, let's revisit the earlier example. First, we translate the pre and post conditions of get into an imaginary specification. It takes an arbitrary integer x, assume ownership of a cell holding x, and then guarantees the same ownership back. Finally, it returns x. Note that the red part encodes the precondition and the blue part encodes the postcondition. For set, in similar, it takes an arbitrary integer x and assume ownership of a cell holding x. Then it calls the unverified callback, obtains a result I, and guarantees ownership of the cell now updated to I. Here's an important point. Unlike pre and post conditions, an imaginary specification can contain executable code like the callback invocation in the spec of set. Moreover, separation logic's assertions may depend on that executable code, as they do here in set, and the code can also depend on the assertions vice versa. To see how such imaginary specifications are used, let's look at the complete example. The program has three parts. The cell library from before is client main, and an arbitrary extra module foo. As before, unverified components are in gray. The main function first calls cell.set with its callback. Then it calls foo, reads the cell's private value with cell.get, and prints the result. We want to abstract this into a program like that. Directly calls the main callback and calls foo, and finally prints the callback's result. Now there's a subtle point in this refinement. At first glance, it might look invalid. So foo can override the cell's private variable by calling cell.set, and in that case, the implementation prints the result of foo's callback, while the abstract program prints the result of main's callback. But the refinement still holds. Here's why. The cell library is absent from the abstract program, so if foo tries to call it, that's undefined behavior on the abstract side, and undefined behavior makes the refinement vacuously true in that case. So the refinement holds even in this case, and I will now show how CRIS establishes it using only separation logic style local reasoning. The first step is to verify the cell library against its imaginary specification using only module local reasoning. In CRIS, we can establish this contextual refinement through separation logic style reasoning fully in iris proof mode. I'll skip the details here and focus instead on the more interesting part, verifying the client. So let's now look at the proof for the main module. We first give main an imaginary specification by simply adding assume cell 0 at the start of its main function. And our goal is to prove a refinement between these two programs using the imaginary specifications of the cell library. With the same cell spec linked on both sides, we prove that main's implementation refines its imaginary specifications. And only its implementation calls cell, so I will hide the cell on the abstract side just to make room on the slide. And again, this simulation proof is also carried out in iris proof mode. Now let's walk through it. We first take a step on the source side and acquire the resource cell 0. That just says the initial value in cell is 0. On the target side, we now have to call set. And because an imaginary specification is itself written as code, we can inline it and run it inside the simulation proof. First, we execute take. If it was on the source side, it gives an arbitrary value, but here it runs on the target side, where it plays a dual role. So we get to choose any value we want, and here we choose 0. And assume cell 0 also plays a dual role. It now releases the cell 0. More precisely, cell 0 is removed from the resources we own. Both sides have reached the same callback. So we run the callback on the both sides at once. When the same function is called with the same argument on both sides, our simulation rules let us jump straight to the continuation and gives both calls the same arbitrary return value, and let's call it R. Running the guarantee operation, we acquire cell R, and then we return to main. Next, both sides call foo at the same time. As with the callback, we jump to the continuation point. Here, we have important point to note. First, by the frame rule of the separation logic, we keep ownership of cell R across the call. This tells us that the value in cell stays unchanged, so we only need to reason about the case where foo does not change it. And what if foo does change it by calling cell.set? Then the encoding of the imaginary specification triggers undefined behavior on the source side, and that makes the refinement hold vacuously. Next, we run this imaginary spec of cell.get following essentially the same pattern. We choose the current value R, release R, immediately acquire the same resource back, and return R. So in the end, both sides print the same value R, and the simulation proof is complete. And we now have two separate verification results, one for the cell and one for the main. Let's see how they compose. First, we have a contextual refinement from the implementation of cell to its imaginary specification. Here we place main's implementation around this refinement as a context. And then we have also proved a second result, that main's implementation refines the abstract version of it when it's linked with the cell specification. And by transitivity, we get this contextual refinement. Then we can place an arbitrary foo module around it as a context. At this point, we can also remove the cell library. This is always a sound refinement because any call to cell will trigger undefined behavior on the source side. And after one more application of transitivity, the only step left is to eliminate the initial assume in main. And this happens automatically through the cancellation theorem we provide. In general, that theorem removes the initial assume along with every matching pair of assume and guarantee. In this example, however, there's no such matching pairs, so the theorem just removes the initial assume and gives us the final top-level abstract program. Now let's take a closer look at the reasoning principles. Here are the simulation rules for the 4 key operators. The rules in the first row apply to the source side, and we use them when verifying with imaginary specification. And everything is dual, I'm sorry. We use that for against imaginary specifications. Take and choose introduce universal and existential quantifier. Assume and guarantee introduce magic one, and separating conjunction in separation logic. The rules in the second row now apply to the target side, and we use them when verifying with imaginary specifications. And everything is dual from the before. Take and choose now introduce existential and universal quantifiers. Assume and guarantee introduce separating conjunction and magic wand. So as you can see, there's duality between the source and target rules. And there's a second duality here too, coming from dual non-determinism. The blue operations use demonic non-determinism, the usual kind, which you can think of as a union of behaviors. And the red operations use angelic non-determinism, the dual kind, with an intersection of behaviors. Take and choose are the basic choice operators for those two forms, and the assume and guarantee are encoded using take and choose respectively. On top of these, we had inlining rules, and that let us inline a function call with a body of the function. These are the key rules that let clients actually use the imaginary specifications. And now, one credit to note here, the core idea of using dual non-determinism to operationally encode separation logic assertion comes from earlier work CCR. But CCR does not have imaginary specification in their mind, and in particular, the inlining rules are unsound in CCR. Supporting inlining of imaginary specifications turned out to be our main technical challenge, and how we solved it is in the paper. In summary, the main novelty of CRIS is the notion of imaginary specifications. Traditional pre- and post-condition style specification describe verified components through logical assertions only. Imaginary specifications go further. They can freely combine those assertions with arbitrary executable code. And that's what makes them especially useful for hybrid verification, where some components are intentionally left unverified. And the overall structure of Chris proof looks like this. We start with the implementation components separately and verify each one on its own, the build up step by step to an abstraction of the whole program. The imaginary specifications are the intermediate layers that let us do this. The two programs in orange at each end of the proof are the real programs. They are ordinary executable programs with no take, assume, or guarantee operations. And what Chris gives us in the end is the refinement between those two orange programs. And that's the result does not mention any of the imaginary specifications in between. So how we define the gray ones, the imaginary specs, is not part of the trust base. Here's a loose analogy. Imaginary specifications are a bit like an imaginary number in math. Look at the example on the right. To prove the two real numbers are equal, we break it into 3 simpler steps that pass through imaginary numbers. The left side works the same way. We break the end-to-end refinement of real programs into several simpler ones through imaginary specifications. And we know of various follow-up works. Some are completed and some are in progress. Completed ones include supporting weak memory concurrency in Chris, and together with prophecy and helping principles, building distributed systems with consensus protocols, and full support for C-Lite with assembly and linking through ComSetM to get end-to-end verification. Support for impredicative higher order predicates without step indexing. Work in progress includes porting to Lean, which is mostly being done by AI, and liveness reasoning in the style of Lilo. So that's all I have for today. Artifact for this paper is available online on Zenodo, and we are also preparing a website and open packages. Thank you.
Questions?
Thanks for a great talk. You only showed example of terminating programs and proof rules that do not really cover instructions that can loop. How do you handle non-termination? Do you use co-induction?
Oh, we're fully supporting. Oh, we are fully. Thank you for the great question. And okay. So thank you for the great question. And Chris is actually using interaction trees, and all the simulation rules are based on PACO and GPACO.
Okay.
So we can all support the non-terminations and conditions.
Okay.
More questions from the audience? All right, I have a question for you. What if the functions you try to inline is recursive? Would that be a problem?
Sorry, I didn't.
What if the function, for example, in your example, if it's not a one-liner, but like the function body is a recursive call, some program and a recursive call to itself, would that be a problem when you're inline? Like, I imagine when you apply your proof rule, you would just like keep inlining again, right?
Oh, you mean the recursion, or? You mean something like recursively inlining?
Yeah. So for example, in your main function, you call the set function, and if the set function is a recursive function, would that be a problem?
Not in general, because as I said before, we have the co-induction principles to handle those kind of recursions. And inlining is not the only way to handle the function calls. We also have the other rules for the function calls. If it appears like identical on both sides, that's the another way to handle those kind of recursive calls.
We can have one quick question from the audience. All right, I have another quick question for you. Can you talk a little bit about the automation situation? Like, do you have any automation built in the framework?
Which kind of automation?
Automation, like, are the users supposed to manually apply those rules?
Oh,
and
yeah.
Manually do the refinement, or there's like.
So for the users in simulations, we provide like almost fully automated reasoning tactics for the users. If you are asking about the
tactics
generating the proof itself automatically. or the like user for the user.
So for example, is it possible to just have a program and then you like a push button tactic that just like try to discharge everything?
Not yet, but the recent AI models are really good at it, and very fast. I mean, they are keep getting better very fast. So
I see. Thanks.
We hope to see that.
All right. Let's thank the speaker again. Our next speaker is Justin, and he will be on the academic job market this year. So if you're hiring, please contact and talk to Justin offline. The talk will be about how to debug proof search.
Thank you. We all know how frustrating it can be to have a buggy proof or program, but at least we have techniques like type systems or debuggers to help us systematically figure out exactly where something went awry. In contrast, when what we're trying to debug is a search procedure that is looking for a proof or a program, we don't have such luck. There's no proof or program to step through in the first place. This has been one of the hardest problems with proof search for decades. Today, I'd like to share with you a new approach for debugging failing proof search based on a general framework that you can apply particular strategies to a given setting. So let's dive into the details. Proof search is ubiquitous and powerful, powering things like database query engines like Datalog, many program synthesizers, type systems like the trait system in Rust or type classes in Haskell, and of course, tactics and interactive theorem provers like ESOP for Lean. And proof search, when it works, is amazing. But what happens when proof search fails? Well, in Datalog, if we ask for a fact that doesn't exist, we may get something like check failed. Or in program synthesis, if we try to synthesize a program for a specification that's unsatisfiable, we might get back something that just says not possible. Now, the Rust community has put in a lot of effort into making really good error messages, but there's only so much that a static error message can do. In this case, I have one missing trait implementation, and that window is showing the error messages that I'm getting. In fact, this is actually just only 3 out of the 11 different errors that I get for a missing trait implementation. Similarly, for ESOP for Lean, when it fails to prove a particular proposition, you can ask it to show you the trace of things that it tried. But for this one missing lemma, this window that I show you right here is the trace that it's going to give you. And in fact, if you can see the scroll bar, that's actually just a tiny % of the trace. So what makes it so hard to explain what went wrong with proof search? Well, to see why, we can represent proof search using this data structure called an and/or graph and understand exactly why it's so hard. So an and/or graph is a data structure that's a bipartite graph consisting of or nodes and and nodes, where or nodes, we'll say, are going to be provable if any of their children succeed. We'll say that an and node is going to succeed if all of its children are going to be provable. In practice, though, the and/or graphs that we're going to be looking at are not so neat and tidy. Here's one that I extracted from a Rust trait error using the Argus tool that Gray et al. Introduced at PLDI here last year. And you can see that it's much bigger. And here's one that I extracted from a proof search from ESOP in Lean. Now, I don't know about you, but I think that these graphs make for beautiful art. But the prospect of trying to figure out what actions I need to take as a user in order to fix this situation fills me with a sort of existential horror. It's just too big and unknowable to know exactly what we need to do. But this is nothing new. Researchers have been talking about the difficulties of debugging these and/or graphs for decades, dating back to at least 1991, all the way up to more modern times. I like the way that Sene and Lazzari put it in 1991, which is as true now as it was then, which is that even though a proof tree, which you can think of as just the and part of an and/or graph, gives a brief account of the solution steps performed during the computation, it only does so for the goals that have been solved in the process. However, it presents neither the goals that have been tried but unsolved, nor the alternative clauses that could have been used to find an alternative solution. A bit more graphically, you can think of as an and graph as a buggy program or proof. And the tools that we have to help us here are things like type systems or step-based debuggers or algorithmic debugging. whereas an and/or graph is more like all possible failing programs and proofs. And the main tools that we have to help us here are visualizing those graphs that I was showing you on the previous slides, or some sort of graph traversal. Maybe we start at the top and do some sort of top-down exploration, or some sort of bottom-up exploration from the leaves. But in practice, we saw that these graphs are very, very large, and it's very hard to know what to do, what actionable steps to take as a user. So what are we to do? Well, I want to point out that these and/or graphs are not just graphs. We'll start from the observation that hidden inside these and/or graphs are mini proof systems that can be poked and prodded, and we can ask hypothetical questions about. So for example, for this tiny and/or graph right here, we have this tiny proof system, and we can say, what would happen if the user were to prove B or C or D? For example, maybe one modification we make is to axiomatize B and C, corresponding to the user manually proving B and C, and we can find out what will happen in that situation. Or maybe make this modification right here that axiomatizes C and D. So our key insight is that we don't want to display or traverse this and/or graph. Instead, what we want to do is we want to navigate the space of modifications to the graph and help the user arrive at one that's going to prove the goal. OK, so let me show you what a concrete example of this would look like when we're debugging ESOP proof search for lean. The modifications that we're going to allow for the user are labeling or assuming possible lemmas. And our goal is going to be derived from a program. The program is going to be derived from a program that's in the test suite for Limperg's and Fromm's ESOP proof search tool. And it's going to be about a big step, operational semantics, and we're going to be proving specifically something about the if-then-else construct, although the details don't matter too much. OK, now, instead of looking at this graph to understand why ESOP cannot prove this proposition, what we're going to do is we're going to have the system help the user navigate possible modifications to this graph. OK, so first thing that's going to happen is the system is going to select a proposition, perhaps this one right here. This proposition is going to differ from the first one in that it's just going to be the forward part of the by implication. Now, for a moment, put aside how the system is going to select this proposition. We're going to return to that later in the talk, so we'll just take that for granted for right now. But now, interestingly, what the user is going to be able to do is they're going to respond with some labels about this proposition. So they'll be able to say that they're willing to prove this proposition manually, that they're not willing to prove it manually, but this proposition should be true, or that they're willing to prove it manually and that this proposition must be used in the final proof of the goal, or similarly, that they're not willing to prove it manually, but that it should be true and it must be used, or they can just say, I don't know. Now, crucially, what we're going to require the system not to show is should be false, because there's no way for this proposition to be false while the first goal is still going to be true. So if the user were to select that label, then their specification would become unsatisfiable. And this is a property that we're going to call in a moment strong soundness. OK, so let's say that the user is not willing to prove this manually. Not sure if it's quite showing up, but let's say they're not willing to prove it manually, but it should be true. Then maybe the system is going to select a new proposition, and the user is going to respond with a new set of labels. In this case, all of the above options are going to be OK to show. And now the user can also select that this proposition should be false, because there are ways to prove those top two propositions while this bottom one is still false or unproven. OK, this turns out to be a critical lemma about the big step operational semantics. And so maybe the user is willing to prove this manually. And the interactive session can end there. But how do we actually achieve this interactive specification refinement process with the kinds of guarantees that we want, where the user is not going to be able to go down one of these rabbit holes of like an invalid label? Well, I've been working on a technique called programming navigation that can be used for exactly these sorts of situations where we need to do some kind of interactive specification refinement process. And we've applied it to synthesizing bioinformatics analyses from wet lab experimental workflows, for creating user schedules for a sparse tensor algebra compiler. But today, I want to talk about how this can be done for debugging failing proof search. OK, but to do that, I need to tell you a little bit about what programming by navigation is. So the idea with programming by navigation is that we're going to model a space of possible expressions or programs, as well as the steps between the programs that you can use to get to each other. In this particular context of debugging failing proof search, these programs are going to be proof system modifications. So maybe this one in the center is just the identity modification that does nothing. Maybe this one is the one that axiomatizes proposition X, and maybe this one is the one that axiomatizes proposition Y. The green stars are going to be the valid solutions, which in this context are going to correspond to proof system modifications that are actually going to prove the final goal. So maybe this one right here that's very close to that one in the center is going to be the trivial modification that simply axiomatizes the goal. Unfortunately, that would be a bit of a rude suggestion to show to the user, because if the user is asking a proof search tool to prove something and it fails to prove it and it says, hey, how about you prove it instead, that's maybe not exactly what the user would want to experience. Instead, maybe what they would want is a modification that's a little bit further out. So this is maybe the desired modification that's going to prove the goal. OK, so the way the programming navigation is going to work is we're going to start in the center here. And if we just imagine a sort of traditional program editing experience, you'd basically be able to get to any of these nodes however you want. But let's take a look at this step right here. If the user were to take that step, then they would enter a part of the program space where there's no way to get back on track to some valid solution. So if we think about what kind of support we would want from a programming system, we would actually want to require that this step not be shown. Instead, we want to show steps like sigma A right here, which are en route to some valid solution. Generalizing a bit, we also don't want to show those two steps right there. And this is the property that I mentioned before of strong soundness, which is that only valid steps are shown. Of course, that's only half the battle. We also want to be able to guarantee that the user can navigate to any of those green stars. For example, if they want to get to 3, 4, or 5, they need to be able to take those two steps right there. And this is a property that we'll call strong completeness, which is that the shown steps are going to be comprehensive enough to be able for the user to reach any of the valid solutions. Then the user can select one of the steps, update the current working expression with that step, and repeat the process as necessary. So, at a high level, the way the programming navigation is going to work is we're going to have a step provider that is going to be providing sets of steps that the step decider, i.e. the user, can select between. And we're guaranteeing that any of those options are going to eventually be en route to some valid solution. So maybe they select this particular label, and the process will continue. OK, so how do we implement a programming by navigation system? Well, there's three main ingredients. First, you need some notion of expressions, you need a notion of validity on those expressions, and then you also need to decide what the steps are and how you're going to be showing them to the user. So we can go through each of these different main ingredients for each of the different cases that I was talking about before, but let's just do it for debugging failing proof search. We've decided that our notion of expression is going to be these proof system modifications, and we've also decided that our notion of validity is that the modification is going to need to prove the final goal. That just leaves how we're going to be providing these steps to the user. OK. Before I talk about what the step providers are, there's one last helpful building block, which is this idea of a non-empty completion oracle. We'll say that the completion of an expression is going to be the set of valid expressions that are reachable from it. So if we take a look at this schematic from earlier, the completion of the expression in the middle is going to be all 5 green stars, and the completion of that expression is just going to be the stars 1 and 2. It turns out that for this particular domain where we're talking about these proof system modifications, we can actually define a procedure phi that is going to compile an expression down to a SAT formula, and we'll maintain the property that phi applied to some expression is going to be satisfiable if and only if the completion of that expression is non-empty. And we have the details in about 1 page in the appendix to our paper, so if you're curious about them, you can take a look at it there. The key takeaway is, though, that we can really quickly check whether or not this completion is going to be non-empty, and that's going to turn out to be super useful to be able to define these step providers with very little amount of code. OK, so first I want to give a sort of warm-up step provider that's going to replicate an existing strategy that we're all going to be familiar with to traverse these trees, which is a top-down step provider. So I just want to show you that we're not losing anything by having all this programming by navigation. In a moment, we'll see novel strategies that are sort of non-topological. OK, the way that it's going to work is we're going to maintain a frontier of labeled propositions, and then we're going to loop over all rules that are going to have a conclusion in that frontier. In this case, there's only one rule. Then we're going to select or collect the set of premises to that particular rule, and we're going to show the user we're going to let the user select which set of propositions they want to label next. So maybe in this case, there's only one option, so the user makes that particular selection, and we're going to repeat the process. Now there's actually 3 rules that have a conclusion in the frontier. And so there's going to be 3 sets of premises for the user to select between to label. And so maybe they perform another selection, and they've chosen this one right here. And you can see that by going through this process of selecting which of the sets of premises they want to label next, they are essentially doing a top-down traversal of the and/or graph. But if that's all we could do, then there'd really not be a point for introducing all of this programming by navigation stuff. And so now let's talk about some non-topological step providers that don't follow the edges and nodes directly of the graph. And the simplest one that we can start with is this idea of a random step provider. So like the name suggests, a random step provider is just going to choose a random proposition and to select to show to the user. Then for that particular proposition, it's going to loop through all possible labels for that proposition. And using that non-empty completion oracle that we talked about a moment ago, it's going to check which of those resulting labels is going to result in an expression that has a non-empty completion. And then it's going to show that to the user to select between. So even though the propositions are going to be randomly selected, the labels are still going to be filtered. So we're actually still going to be able to satisfy our strong soundness. Now, I'm not going to stand up here and say that random is the best step provider ever, because as a user, it would probably be quite overwhelming to just be like bombarded with a bunch of random propositions to label. And so to motivate our next step provider, so the user can select and this process can repeat. But to motivate our next step provider, I want to go back to that large angular graph from Aesop and Lean just a moment ago and zoom in a little bit to right here. So it turns out that this particular proposition right here is actually very special. And there's essentially no way that you could know this just by looking at this visualization. But by special, I mean that if it's assumed, then the goal is going to be proven, and most valid labels for this particular proposition actually happen to axiomatize that proposition. So all else being equal, if we were to show this proposition to the user, there's a very high probability that the interactive session would actually end right there and we'd be done. And so perhaps this is a proposition that we would want to show to the user. Using that non-empty completion oracle that I mentioned a few slides ago, it's actually really easy to essentially compute a score for each of the different propositions that's going to be capturing this idea of how close we're going to be to ending the interactive session. And so we can just apply that score to each of the propositions, and then instead of randomly selecting a proposition, we can actually just take the argmin of the scores of those propositions and show that one to the user. So just by subbing out essentially one line of code, we can get a totally different user experience with our step provider. And that's, instead of random, that's what we call our cut step provider. And that's actually the step provider that we used to have that 2-round interactive session earlier in the talk. Those were the propositions that were selected with this strategy. OK, so we saw our notion of expressions and validity and a couple step providers. In the paper, we define a bunch more step providers. For example, one's based on information theory, when you use like expected information gain about like asking the user about certain propositions. We also have some based on sort of traditional why not provenance from the database theory literature, and so on. All of these are going to be super easy to define using this non-empty completion oracle that we just need to define once up front, which for this particular setting we defined via compilation to SAT. So with that, I'd like to thank my collaborators, Marlena, Max, and Sarah, and I'm more than happy to take any questions. Thank you.
Go ahead. Hey, Adam Japala from MIT. The AND/OR structure seems very propositional, and I'm trying to figure out what this means for first-order logic and beyond. Probably relatively easy to handle for all that below the bar of what you're trying to prove, but exists below the bar. How does that manifest?
Yeah, absolutely. I think that's totally an open question. So for right now, I think that you even start to run into this even with Aesop, where you might have like different existentials that it needs to like insert to like complete the proof search, and we don't really have a good answer of like what that would look like. But if we can define a suitable data structure that's going to be encapsulating those sorts of quantifiers, then perhaps we may also be able to define like suitable modifications to that data structure. Yeah, it's a great question.
Thanks.
Thanks.
More questions from the audience? I have a question for you. So I imagine different step providers will be good for different workload, right? Like, do you have, I don't know if you have run those kind of experiments, but do you have some insights on like what kind of step provider will be good for, what kind of workflow? For example, if I'm doing like Rust trait error debugging, or I'm doing still improving using tactics, and maybe I should use top-down approach in this scenario, and so on.
Yeah, that is a great question. Thank you. So I think that like I was finding, I don't have any like empirical results to say like exactly like one is better than the other, but just like in using it, I think that the cut step provider turned out to be like quite useful for these sorts of things, and for Lean. And then for for the Rust trait errors, it turns out that like all of these step providers that I was mentioning are actually compositional. Like you can kind of like combine any of them with each other and you'll still satisfy all of the properties. And so something like cut or maybe max information gain to get like to a certain part of the tree for a Rust trait error, and then using maybe a bottom up and top down step provider to sort of like explore the traits around that one seems like it could be a sort of promising strategy. But yeah, I think that it's going to super depend on the domain. Thanks. It's a great question.
Cool. Thank you. All right, let's thank the speaker again. All right, this is our last talk for the session. So Nick will tell us about Project Everest?
Does that work? It's on, I guess. All right. Thank you all for coming. I'm going to tell you about Project Everest, and it's a Toplis paper. It's kind of a retrospective paper, and the subtitle of it is Perspectives from Developing Industrial-Grade High-Assurance Software. Project Everest was a multi-institution collaborative effort that started in 2016 between Microsoft Research, INRIA, Carnegie Mellon University, and also a Microsoft INRIA Joint Center, plus several other institutions. We were aiming to build and deploy provably correct, secure communication software, and I'll make that a little bit more precise in a bit. The Project Everest team, I think one thing that was unique about it was that it involved people from several different areas, and four main areas, I think. So there's folks from programming languages and verification. We had folks whose expertise was in security, cryptology, and also systems and engineering. And this was the core Everest team. We were also spread across several geographic locations, the Microsoft Research Labs in Cambridge, Redmond, and in Bangalore, but also INRIA and CMU, as I mentioned earlier. That was our core team, but we really had contributions from many other people. And that's I think that represents maybe around 50 people in that list. And I see some people here from that list. So thanks to everyone. So for this talk, I'm going to tell you about what we did, why we did it that way, some things that worked and some other things that didn't, some reflections on that, and also maybe give you a glimpse into the future. That said, we wrote this paper about 8 months ago, and the future has changed since then, so I'll also reflect on some of that changed future. The paper is about a 60-page paper with maybe 230 citations and so on, so there's lots more on the paper with some reflections and anecdotes and so on, so I encourage you to check that out too, if you're interested. So what we set out to build in 2016 was, this is a picture from the proposal we made at MSR around that time. At that time, Jeanette Wing was the director of MSR, and she had come to MSR from the NSF, where she had been running the NSF Expeditions program, and she thought to create a similar expeditions program at MSR to foster sort of large collaborative projects. And she sought applications. MSR usually doesn't have grant proposal applications, but Jeanette, for this expeditions process, sought project proposals from us, and this was a picture from that proposal that a few of us wrote. What we promised to do, or what we aimed to do, was to build verified components for the TLS and HTTPS ecosystem. If TLS is the protocol that was previously called SSL. It's the thing that underpins HTTPS. When you go to your browser, you see the little green lock there. That's because that connection is authenticated and encrypted using TLS. Because this protocol is kind of the centerpiece of internet security, we thought it was valuable to try to build a verified implementation of it. And our goal was to build a drop-in replacement of components that comprise TLS, with performance parity being a primary goal. Some 5-6 years later, this is actually what we ended up building. And it's going to take me a while to explain this picture. And for a big chunk of this talk, I'm going to sort of walk you through this picture. But just to give you a high-level view of it, all of these software components represent about 1.3 million lines of F-star source code. We also had some auto-generated code produced by various metaprogramming tools and code generators, but that's not included in this 1.3 million source lines. These are lines that the team wrote by hand. Building these 1.3 million lines of F-star takes about 2 hours on a build server with 24 threads. That build issues about 66,000 SMT queries, representing about 600,000 separate proof obligations that were discharged by SMT. Plus, there were many more proofs that were done by tactics and higher order unification and normalization and so on. But so this is just the SMT solver count. As I said earlier, a key goal of Project Everest was not only to build this verified software, but to also deploy it. And I'm going to tell you a little bit more about the deployments, but we have our code today runs in Windows and in Azure, in Hyper-V, in Python, in Firefox, and in Linux as well. So let me first sort of reflect on some design choices and principles that led to the way this project was conducted. So the first thing we set out to do was we were very clear that we wanted to build verified software from scratch, rather than trying to verify existing implementations. Primarily because verifying existing implementations is considerably harder, and we were keen to exploit designing software with proof in mind to try to reduce the proof overhead. We wanted to work in a setting with high expressive power. We anticipated using things like meta-programming and embedded DSLs and so on. So we wanted to be in a logic that was dependently typed in higher order. And another sort of bias, I suppose, is that we preferred automation and scale over TCB minimization. Of course, we wanted to minimize the trusted computing base, but we prefer to go for automation rather than the smallest TCB possible. This meant we were willing to heavily use SMT, as I already pointed out earlier, primarily using Z3. And we were also willing to rely on transpilers to transpile our verified code into a form that we could deploy in other settings. So, and for that, our goal was to produce code in C and assembly, both for performance and for ease of deployment. So with those principles in mind, maybe I can give you a little bit of structure into this big picture, which is that a key principle of the project was that we were going to co-develop the programming tools with its applications. So in this lower part of the figure, we have F-star and the related tools and methodologies, the core programming language as part of the project. And on top of it, we had three main classes of applications: cryptographic algorithms, secure data formatting, and protocol proofs. Zooming in a bit, the core parts of our programming language technology were F-star. F-star in 2016 had just gone a significant revision around making it a fully dependently typed language. And the evolution of F-star was, now 10 years later, was heavily influenced by the Project Everest applications, and F-star really has grown and because of Everest. We used Z3. F-star is coupled with Z3 for proof automation, so it's dependently typed, but it produces verification conditions that by default it discharges to Z3. In order to make F-star capable of handling these kinds of the effectful programs that we wanted to write, we developed this technique called Dijkstra monads to embed program logics for effectful programs inside F-star. And using that, plus some other features, we also built a tactic and meta-programming system for F-star called Meta F-star. And underneath this, we had a tool called Caramel, which was our transpiler that transpiles verified effectful F-star code in a first-order fragment of F-star to several backends, including, at the time, primarily C, but subsequently Caramel also emits WASM and Rust. And I'll tell you a little bit about the other backends in a minute. On top of this core layer of F-star, we built several embedded DSLs. The first one was called Veil, a deeply embedded DSL for verified assembly language. And Veil programs could be they could be just pre-printed as x86 assembly. So there was a semantics for a fragment of x86 assembly in Veil, and the Veil program logic was developed foundationally against that semantics in F-star. The other language we built was a language called Lowstar, a shallow embedding of a DSL that allowed you to program against a C-like memory model with proofs using explicit dynamic frames. And Lowstar programs could then be transpiled to C via Caramel. We also stacked DSLs. So on top of Lowstar, we built another DSL called Everparse, which was a verified parser and serializer generator. And recently, we've also retargeted retargeted it on top of a newer DSL called Pulse, which is one of 2 concurrent separation logic DSLs we built in Project Everest. The other one was called Steel, and Pulse is its most recent successor. Interestingly, while we aim to deploy primarily the applications we built, it turns out that we also deployed the tools that we built. So today, all of these tools, well, most of them, Everparse, Lowstar, Pulse, FStar, Z3, and Caramel, all of these are packaged into a build extension mechanism that is installed as part of the dev environment of all Windows developers. Now, moving to the applications, the first class of applications we built were verified cryptographic, a provider for verified cryptographic algorithms. Hacklestar is a library that was led by folks at INRIA, and it's a portable library of verified crypto primitives and constructions in Lowstar. Veil was used to build a library called VeilCrypt, which is using which we built verified optimized x64 crypto for various TLS-specific cipher suites, including especially AES-GCM, which is a hardware-accelerated authenticated encryption primitive that's key to running TLS efficiently. On top of that, we packaged Hacklestar and VeilCrypt into a cryptographic provider called EverCrypt that lets you multiplex between the various implementations depending on what processor you were running on and so on. The whole thing is with EverCrypt, Hacklestar, VeilCrypt. These 3 components are probably the single largest component in the Everest stack. It represents almost 250,000 lines of FStar and Veil source and produces about 135,000 lines of executable C in assembly. This proof-to-code ratio is, I think, quite favorable, partly because cryptographic code is, fairly regular, and we developed proof techniques to be able to do these proofs efficiently, but also because we heavily used metaprogramming and higher-order abstractions to keep the proof overhead low. Crypto from Hacklestar and EverCrypt is now, and VeilCrypt is deployed in various places, including in Firefox, in Python, in parts of a Linux VPN, and also in an election library, secure voting library called Election Guard. An interesting kind of side project that became a big part of Everest was the application of Everparse and secure data formatting tools to harden attack surfaces in large parts of Microsoft software, including in Windows and Hyper-V. It turns out that parsing binary formatted attacker-controlled data is a big source of security attacks, and replacing those parsers with verified code from Everparse has been a large ongoing effort in our research group. We also produced the first formalization of ASN1 and X509, which are the certificate formats used in TLS. So going back to the attack surface hardening, since 2021, Everparse produced parsers run in Windows and Azure. And today, every network packet passing through Hyper-V in the Azure cloud has its virtualization envelope first validated by Everparse-generated code. Finally, we had the protocol stack on top, which was primarily this library called MeTLS FStar. It had the first verified implementations of the TLS 1.3 and quick record layer protocols. And in doing so, we found and fixed a downgrade protection flaw in the TLS standard itself as the standard was being drafted. The MeTLS FStar was also deployed in Windows as Microsoft was implementing the quick protocol in around 2019 or so, although it doesn't use it today. I should also say that there are parts of this that we didn't quite finish. So there's a part of MeTLS FStar, which is the handshake of the TLS. We didn't actually finish proving this correct or secure. But we did develop a technique called state-separating proofs to model the kind of cryptography needed in MeTLS FStar. And that technique led to the creation of SSProve as part of Project Everest. And SSProve was recently used to prove the cryptographic security of the TLS key schedule as part of the BERTI project. So that's a lot about what we did. So maybe a little bit about some reflections. As I said, the main thing we were doing was trying to co-design language and applications. And I think this was an interesting style of doing work. It kept the language design and implementation honest. It had to work at scale. But coping with the change as building our applications while the tool was changing was also very hard. Some of the things that we did, maybe the most prominent thing, was we built a very sophisticated CI system to allow us to evaluate changes as we made them, both on the application side and on the library side. But proof maintenance, as we all know, is a lot of work. We also use SMT-based proofs. This allowed us to scale rapidly with I think, a fairly modest proof-to-code ratio. I think it makes the learning curve shallow at first, but it becomes steeply sharper as you go to more complex proofs. And opacity and instability of proofs was a big problem. That's a problem that us and others continue to work on. There's solver instability is one, talking with authors of Z3 and some others, I think we believe that solver instability is not inherent to SMT solvers. Some of them are actually due to just solver bugs. I think I'm a little short on time, so I want to just jump quickly to some reflections. Getting things to work for industrial deployment takes time and luck. It requires working closely with engineering teams, and developing components piecewise is easier than trying to deploy large components all at once. And but the point I want to really get to was, doing this kind of proof, is it really cost effective? So this took us, building this entire stack maybe took us around say 50 to 100 person years of PhD level expertise. There's 1.5 million lines of code and lots of reusable bits, but is this level of effort really worth it? So I think one thing that we go to some lengths to discuss in the paper is that you got to choose your targets well. Security critical components are worth doing, but maybe not everything is worth doing if the cost is really this high. But things are changing, and if we think about cost effective, well, the costs are different today. So I mentioned to you that there was this part of MeTLS that we hadn't actually proved correct, and I knew I was going to give this talk. So about 2 weeks ago, I got an agent to program this part of the TLS 1.3 client and get it to prove the handshake correct. And in about 2 weeks, spending about $3,000 in tokens and producing about 125,000 lines of code, we now have a TLS 1.3 in a very particular profile, a one round-trip handshake for a particular kind of a cipher suite, producing about 120,000 lines of verified implementation in Pulse with a 5,000 line spec for the TLS state machine, and about 384 lines of spec produced by the agent in Everparse to generate verified parsers and serializers, and about 25,000 lines of executable C code at the end of the day. This was entirely agently written in 2 weeks. And what is proven is a functional specification relating the raw bytes on the TCP channel to a state machine spec of the TLS state machine, including the wire format of the TLS messages, and relating this to the application level channel, the bytes that the application sends on the TLS channel. And this is related to the imperative implementation in Pulse via a state machine refinement. There's many caveats. This is only a functional correctness theorem. It does not model any adversary, and it's not a cryptographic result. The theorem covers only one main scenario, the most common scenario for a TLS handshake, not every variation that it supports. It still uses an unverified certificate validation component from OpenSSL, so we did not integrate in this the ASN1 and X509 certificate chain validation. And it reuses components that we had previously in Everest. So it reuses Hackle star cryptography and so on. But still, producing proof at this scale in 2 weeks is, for us, just transformational, I think. So attempting some takeaways from this, I think, to be honest, we're all still trying to process what it means for the cost of proof to have plummeted as far as it has. So just attempting some takeaways. I think the first thing I'll say is that our program verification tools work, and agents are fluent in it. So far, it seems that these agents are able to accelerate experts, and it's not yet fully autonomous, but I think it also provides a boost to non-experts. And exactly figuring out how to control this remains to be seen. Something that we've been thinking about is, if we aren't really doing the proofs ourselves, at what level should we be thinking about this? And these days, I've been wondering about proof-oriented architecture, some way in which to enable steady, auditable agentic progress, allowing humans to audit progress as the agents do their work. How do we figure out how to teach humans and agents specification style and spec review? And this, I think, is still very open-ended, and I would love to talk to some of you about this. And the other thing I think about is, how do we build workflows for agentic program proof, some way that makes the orchestration of these agents predictable, cost-effective, auditable, and durable? I think that's also an interesting programming languages topic. So now this is my last slide. So leaving you with some reflections. So 10 years ago, I think there were at least 3 projects come to mind that had a similar sort of spirit. We were doing Project Everest. There's a group of people, many of you whom I see in this room, doing deep spec. There were others doing a project called Verified Scion. And the sentiment then was really, I think, it was time to go big, trying to use the advances that we had in program logics and our proof tools, and really to try something ambitious. Well, I think the time has come for us to go way bigger. Our community has the tools and techniques that work, and now we have agents to help us power it, and it's time to set ambitions that are much higher. But exactly where to place those ambitions, I think it would be really interesting to discuss what is possible and where we should go. I think part of it means going harder. That is, I think we know how to build large verified systems if we were to start building them from scratch in our proof-oriented tools. But maybe going harder means being able to verify existing systems at scale in all their complexity, using systems that are built in C and C++ or CUDA, Python, or TypeScript. Can we get our verification tools to handle systems as they are built in the wild? That's one level of going harder. The other is maybe we should be also going for harder properties. Can we build scalable techniques to prove liveness, complexity, performance, availability, auditability? That's another dimension that I think this community could take on. There's a third challenge, which is despite trying to go, while trying to go bigger and harder, we also have to somehow go faster because agentic software exploitation is upon us now, and I think it's on us to quickly find a way to respond to this, and I think program proof might be one definitive way to address these problems, but it's urgent, and we have to act quickly. I think this calls maybe for us to also think again about large, multidiscipline, multi-institution collaborations. If you're interested, I'd love to team up, and please reach out. We'd be excited to think about what some big challenges for us could be. So that's it. Thank you.
All right. I don't think we have time for questions, but feel free to talk to Nick offline, and I'm sure you have a lot of questions to ask. But thank everyone for attending this session, and also thank Kirby for handling the AV stuff. Enjoy the rest of the conference.
Go ahead and unmute it. All right, folks, let's take our seats. We are at the last and therefore best, most treasured session of PLDI. This session is going to be about data processing pipelines, and that's sort of an opportunity to use very high-level information to get good performance and better understand our code. And so we're going to start off with a talk from Ziteng, related to a paper from OOPSLA 25. And he's going to tell us a little bit about how we can use homomorphisms to better understand our code. Please.
Thank you, Pavel, for the introduction. Can you guys hear me? Okay, great. Okay. Hi, everyone. My name is Ziteng Wang, and from UT Austin. Today, I'm going to present our work, Homomorphism Calculus for User-Defined Aggregations. A little bit context here. So modern analytics run on frameworks like Apache Flink and Spark that aggregates massive tabular data. People call them data frames. And then there are two basically operations you can choose from. The first one is built-in aggregations. They are basically a set of standard operations, very handy to use and also highly optimized. On the other hand, there are also user-defined aggregations. That's the place where the developer can express their own domain-specific logic, such as custom statistics or telemetry summaries. And nowadays, user-defined aggregate functions are everywhere in the large-scale analytics. So how do we implement such custom aggregation logic here? Well, essentially, UDFs are just a fold here. That means that it consists of two parts. The first part is the initial state, which is the state you will have at the beginning of the computation. It also has the so-called accumulate function, which basically takes in the current state and the current input, and then it will force the next row as the input into the state. If you expand the definition of fold, that will be the form that we all familiar with here. So to implement a UDAF, init plus accumulate function are like the minimum things you need. But most of the time, the UDF also includes a merge function, as both Spark and Flink supports, that basically allows parallelization and incrementalization. This merge operator takes two intermediate state buffer results, B1 and B2 shown here, and then it will combine them and produce a new result state buffer. To see them in action, let's first take a look at the incremental computation. Imagine that you have some chunk of data that you already processed and you already have the result through running the UDF computation. And then you have some newly arrived data such that you wanted to compute the new output by, well, combining the old data and the new data frame. The problem is that the input data you already processed might be a large data frame, and you don't certainly want to repeat the work you've already done here. So instead of running the computation again, we just run the aggregation on the newly arrived data and get the partial state. And using the merge operator, we were able to merge the previous state with the new state and get the final result. For the case of parallel computation, the input is partitioned into different shards that get processed over multiple nodes. And then each node will have their own intermediate result. And this result state buffer will be repetitively processed by using the merge operator to get the final result. We saw now merge functions are useful, but what does it mean for the merge to be cracked? Well, basically, it needs to satisfy this algebraic law I show here. Here, it says that the UDF computation P is the data frame homomorphism if there exists a merge operator such that, well, for all of the data frames D1 and D2, the result of running UDF on the D1 concatenates with D2 should be equivalent to the result of first individually run the aggregation over two data frames and then use the merge operator to combine them. On the other hand, if the correctness condition isn't satisfied, well, bad thing can happen. Here, the wrong merge function will corrupt the result. As an example, let's consider if the merge output depends on how data was processed and merged. In that case, if the order of how you merge data is dependent for the output, then this will introduce non-determinism in your computation. That means depending on the order, like you're merging the intermediate state buffer, that give you like a different output. In distributed execution, we don't have control over how the order, like all the intermediate state buffers are merged. In that case, that might give you incorrect output. And we know that developers write these merge functions by hand, so it's very easy to get wrong. In fact, in our evaluation, we collected 45 UDF functions from GitHub, and we did find 9 out of 45 of them has bug. Okay, and what makes the problem even worse is that the merge function does not always exist. Let me show you this example. So this simplified UDF basically aggregates on the events from a website that is tracking all of the user clicking and all of the events. And if you take a look at the third line, it basically says that if the current event is checkout, then you update checkout count to be event count. Well, can a merge function exist for this UDF? Well, the problem is that, as you might already noticed, checkout count snapshots event count at checkout event. So every time it's just override the checkout count. And there's no way you can recover the previous checkout count at a time we are merging them. So searching for a merge is basically futile here. You will waste time like searching for something that doesn't exist. So in this work, we wanted to solve this problem. Given a UDF-P, we wanted to see that if the UDF-P is the data frame homomorphism, then we wanted to synthesize a merge operator that serves as the witness of the homomorphism property. On the other hand, if P is not a data frame homomorphism, we want to prove that no merge function exists, and we will warn the user that if they write any merge operator, that is unsafe. Either way, the developer gets a trustworthy answer so that we can better assist them in writing custom aggregations. So what are the challenge here? Well, to synthesize merge, we need to first verify the correctness given a merge function. Let me tell you, like, this is a challenging relational verification problem because of the following reasons. First, as you might notice, this property as a specification involves universal quantification over all data frames. And secondly, the specification includes the reasoning over concatenation of arbitrary data frames, which may have, you need to reason more semantics or concatenation here. And finally, the UDF computation itself here, P, is unbounded over the input data frame. So this makes a really challenging relational verification problem. Our solution to this problem is the introduction of normalizer, which reduce verification to a local parole property rather than reasoning the arbitrary data frames. This is based on the observation that a cumulative function f needs to satisfy a generalized commutativity condition with respect to the merge operator O+. Let me tell you more about generalized commutativity here. We call this commutativity generalized because it relates to functions of different input parameters. Here, B1 and B2 are two intermediate state buffers, and then we first sequence them into the merge function. The output now will be sequenced into the cumulative function where the other input is the current row R. This will be equivalent to the alternative execution path where we first do accumulation on B2 and R and then use merge function to merge the, well, partial result from B1. As you can see here, none of the tau R and tau here are, well, the type of data frame. So we are not reasoning about data frames here. Instead, we are reasoning about the input per row and the state buffer. The key result here we have is fold is a homomorphism if and only if the cumulative function satisfies those properties I showed here. And I started to introduce the second condition, which is the identity law. This is the side condition that basically states that merging the empty partition does nothing instead of changing the result. Cool. So now that we have a local way of verifying, this also makes synthesis problem simpler. This is based on the result. A UDF is homomorphism if and only if its accumulator function f has a normalizer h, and the normalizer is the merge operator. So instead of finding the merge operator, we can just find the normalizer function h with respect to the accumulator function f. Now, the most natural thing to think about is, well, we can probably use some off-the-shelf Saiga solver for normalizer synthesis now that we have this tractable per row synthesis spec. But we have two problems here. First, the search space for Saigas could explode when the state has many fields and nested collection, as in this example. And secondly, searching for a non-existent merge operator never terminates. So we may waste a lot of time and didn't get the result of warning the developer that this UDF isn't homomorphism. So we designed our tool Inc. such that it will take an input UDF-P, and then it will use a series of proof rules to refute the existence of merge function at first. And then to make synthesis tractable, we use type-directed decomposition to break down the synthesis problem into simple subproblems. Let me start with the first idea. The first idea is the proof rules for refutation. We want to reject hopeless problems before synthesis. And we design a series of necessary conditions. As an example, here is the condition we're using to showcase. So this basically says that the condition where the cumulative function is inconsistent to support a merge operator. Let me explain this in detail. It says that there exists the state buffer S and the input X, such that if you apply the cumulative function on this initial state I, then it preserves the initial value the same. But if you apply this on another state S, then state does change on this accumulative function. That means that the order or like the current state you are applying does affect how the cumulative function will update the result. So this accumulative function is inconsistent. There's no normalizer for it. And now we are able to synthesize, but synthesis is still hard. That's why we are using our second idea, type-directed decomposition. This is based on the following observations. First, UDFs are often made of multiple smaller operations combined. And second, a normalizer for a composite type split into smaller normalizers. What's even better is that solving smaller normalizer, the problem of solving smaller normalizers are independent to each other. So naturally here, we will be able to decompose normalizer synthesis to independently solvable subproblems. Here's an example to see that in action. Here's the normalizer state we just seen in the previous slide, and it is made of 3 items. The first 2 are scalar values, integers, and the third one is a map of just a collection. Here, our type-based, type-directed decomposition is able to decompose the problem of synthesizing the normalizer into different scalar leaves problems. That is what the green boxes are highlighting, H1, H2, and H3. And then we can use inductive synthesizer to find the normalizer for those scalar leaves. On the other hand, once we have these scalar leaves, we're able to use derivation rules to instantiate larger or more complicated normalizer from those leaf normalizers. For example, H4 is instantiated from H3, and H1, 2, and 4 can make together to have the normalizer for the root normalizer here. So here we are searching only the scalar leaves, and everything else was derived structural. To recap, we have 3 key ideas here in our work. The first one is we reduce the synthesis and verification problem from using the full data frame property to a local Perl property. And secondly, we designed the proof rules for refuting homomorphisms. And finally, we use type-directed decomposition to make synthesis scalable. In the paper, we give a homomorphism calculus that captures the 3 key ideas. For the evaluation, we collected 50 tasks from GitHub, and 45 of them are homomorphic, meaning there exists a merge function for them, and 5 of them are non-homomorphic. Interestingly, all of the UDFs comes with developer-written merge function, but we know that 5 of them actually, they are non-homomorphic, meaning that the developer-written merge function is necessarily buggy. And forgot to mention, these tasks are either Apache Spark or Flink UDF implementations. So our prototype tool, Ink, was able to synthesize 43 out of 45 merge operators. It is able to successfully refute all of the non-homomorphic benchmarks and significantly outperforms the existing synthesis baselines. For the ablation study, we evaluated whether our key contributions in merge synthesis synthesis are significant for the success of Ink. And the evaluation result says that all of them are key to the success of our tool, Ink. For refutation, we turn off all of the refutation rules, and we just rely on CVC5 Saiga solver to report the problem is infeasible. But that one can only refute 2 out of 5 non-homomorphic benchmarks. So that's all for Ink. I'm excited to share our work with you today, and I'm happy to take questions.
Right, well, so let's take questions at the 2 microphones. And if you wouldn't mind saying your name and affiliation.
Okay. Hi, it's Caleb Stanford, UC Davis. Thank you very much for the very nice talk. So in practice, developers do write merge functions and reduce functions that are not necessarily deterministic, sometimes non-deterministic. For example, things like an argmin or an argmax is a good example, where maybe I don't really care which minimum I return as long as it's one of the minimum elements. I was wondering if your techniques to synthesize merge function or determine if it's possible would generalize to this non-deterministic or non-functional setting.
I think it does generalize to this particular setting. So if I understand correctly, you are saying some particular value are not necessarily required to satisfy this property. In that case, I think the developer will be able to extend our prototype tool to ignore certain fields and only say like this is particular field that we care about, and the other non-deterministic things will be ignored. Is that what you're asking?
It's probably a little bit more general than that, but that may handle some cases. We can also take it offline.
Okay.
Yeah, but thank you for the nice work.
Yeah, thank you.
Hello, I am James Song from Stanford. First of all, thank you for the talk. It was very interesting. And so my question is, it seems that you are unconditionally decomposing your result type into scalars, but what about for accumulation functions that don't necessarily operate on multiple fields at a time, right? It seems that would impact completeness, and also do you have any argument for completeness or no?
That's a really great question. In our paper, our rule for decomposition, it does support the case where you have dependencies between all of the fields. In that case, my answer is no, you cannot decompose them. So right, this example we present here is really like a simplified version, but I agree, like in that case, we can just decompose whatever we can, but leave the undecomposable part behind.
Thank you.
Yeah.
All right, thank you again. It's your time. Next speaker will be AJ. He will be telling us about a project on using pruning inside database traversals to try to make those database traversals faster with applications to things like graphics and all the classical databases. And I think the title of the project itself says it all. Small trees are beautiful. AJ, as soon as you've... All right, please.
Does this work? Cool. All right. So thank you for the kind introduction. Yeah. So I'm AJ, and I'll be presenting our work on Bonsai, a compiler for queries to prune tree traversals. And this is joint work with my lab mate Chris, our advisor Fred, and collaborators at Stanford, MIT, and Adobe. I want to motivate with a simple motivating example of a range query, which is a fairly standard database operation. I have a set of numbers illustrated here on a number line, and I want to collect all of the values in between some low value and some high value. This query can be accelerated a number of ways, and via a number of different tree types, but I'll illustrate this example with an interval tree. So I can, and in Bonsai we represent this via a simple filter over a set of integer values x, and we select elements from that set between low and high. Via an interval tree, we can accelerate this query by recursively constructing intervals that contain the subtree, the values of the subtree beneath them. And we can accelerate the range query by slicing this interval tree via the low and high interval values. In functional notation, this gets lowered into a tree traversal over an algebraic data type tree, where when we match on the tree type and we see a leaf variant, we evaluate the filter predicate, checking if x is within the range, yielding the singleton set x if x satisfies it, and otherwise an empty set. For an interior node that stores a left and a right subtree, as well as an x low and an x high value, we first check whether or not the filter predicate is always true, which is true when x low and x high are fully contained within the query interval. And if so, we scan the subtree T. Otherwise, we check the case where the filter predicate is maybe true, and we union the subtree results, the recursive results of the left and the right subtree. If the filter predicate is not always true or maybe true, it is never true, in which case we return an empty set and we don't recursively visit the subtree. For the tree on the right here, the root node lies in the maybe case. The interval at the root node overlaps with the query interval, and so we recurse into the left and the right child. The left child hits the always case. The AD interval is fully contained within the low to high interval. And so we can scan that subtree without needing to reevaluate the filter predicate on the remaining, the left and the right subtrees of the green node. And lastly, the right subtree of the root hits the always case. This interval does not overlap at all with the query interval, and so we can prune this node. And this is the sort of general structure of using a tree to accelerate a query, specifically like an augmented tree. But filters and range queries are not the only things that you can accelerate. So suppose I wrap the filter in a count operation, which is fairly standard in a database system. We can take the structure of the filtered traversal and use it to compute the fuse result of the count of the filter. And so what that looks like here is we change the return type to be a simple integer value. We change the leaf case to return 1 if the filter predicate is satisfied and 0 otherwise. The scan case actually counts the size of the subtree. The former union actually takes the sum of the two subtree results, and returning an empty set returns 0. And this is how you perform a fused operation on a tree. But counts and filters or counts and range queries are not the only operations that we care about accelerating via trees. And in Bonsai, we support count and a more general notion of filter, as well as any and all, which are sort of binary forms of filter, a more general form of reduction operator for associative and commutative reductions, as well as idempotent operators like argmin, argmax, min, and max. We also support product, which is going to allow us to represent an interesting class of joins. And while we have sort of sub-languages for expressing the metrics for argmin and max, I'm not going to talk about that today. So if you're interested, look at the paper. But I will talk about our predicate language, which supports Boolean combinators, arithmetic combinators, as well as geometric combinators. So we can check whether one geometry contains another or a geometry intersects with another, and so on and so forth. And this is going to let us to represent some really interesting algorithms from the spatial query community, including ray tracing, in, closest point queries, and collision detection. And so Bonsai takes this high-level query specification, as well as an algebraic data type representing the tree data structure, with explicit annotations. And those annotations look like tagging data, scalar data, to be within a low and a high value, or tagging geometric data to be within a bounding volume, for example, an axis-aligned bounding box. But it also looks like more general reduction operations, like storing the count of a subtree or the minimum ID of a subtree in fields C or M, respectively. And Bonsai takes these two specification languages and compiles to a tree traversal IR that enables us to do efficient fusion of the operators, as well as a technique we term predicate analysis, which is all about taking this predicate sublanguage as well as the bounds annotations and generating these always, maybe, and never conditions that I showed on the previous slide. And then we compile to C++. So that's sort of the high-level overview. And before I get started talking about fusion and predicate analysis, I want to talk about what the state-of-the-art in generating tree traversals is. And this is a bit of a misleading slide, because the state-of-the-art before Bonsai was that you write your own. If you have some set of queries that you want to implement, or even some fused set of queries, before Bonsai, you had to implement that set of queries times every single tree that you want to use in your database management system or other accelerated query system. Bonsai's techniques enable linearizing this dependency, so you can now write a batch of queries a single time and a tree specification a single time, and Bonsai handles this quadratic dependency for you. And so what that looks like is we take our high-level range query expressed as a filter here, as well as a declarative tree specification for implementing the integer set. And so that's shown here. The type tree has two variants, a leaf node that stores integer data, and we explicitly tag that data as data to be represented within the set. And an interior node, a recursive variant that stores a left and a right subtree, as well as this x low and x high value with data explicitly tagged to be within that scalar range. The Bonsai compiler is a bottom-up code generator. And so we take this tree specification and we take this query, and we first generate a base iterator for the base set. And so to iterate the base set, we produce the following tree traversal, which matches on the tree type. For any data, for any variant with an explicit data label, we yield that data. And for any recursive node, we scan that subtree. If we want to take this base iterator and generate the filter that I showed previously, we simply rewrite the yield of x to be guarded by the filter predicate, and we rewrite the scan of the subtree t to be wrapped in an always condition for the filter predicate, or in the case of the maybe condition being satisfied, we union recursion on t. Otherwise, if it's not always true or maybe true, it's never true, and we return an empty set. For this particular example, the range query, the always and maybe conditions are exactly the interval containment and overlap respectively. And so the Bonsai compiler stamps in those conditions. Now, if we want to, once again, implement the count of this filter, we can apply small local changes. First, we change the return type. We rewrite yield to be 1 or 0. We rewrite scan to be the count of the subtree, and we rewrite the recursive union to be the recursive sum. And then lastly, the empty set becomes 0. But we can actually accelerate this query even further with Bonsai's machinery, which is if we extend the interior node to additionally support a count augmentation, shown here, we can rewrite the always case to, instead of recursively count, we can just return that memorized value. And hopefully the intuition I'm giving you here is that fusion in Bonsai is a simple local rewrite of yields, scans, and froms. And that is exactly how the code generator is structured. So we iteratively rewrite these yields, scans, and froms. What the rule for lowering a filter of an arbitrary predicate P over a set S looks like is we first lower the generator for the set S, and we rewrite any yields in that generator to be guarded with the predicate P. Similarly, scan gets guarded with an always P predicate. If we can't prove that the predicate P is always true, then we check if it's maybe true, and we union the subtree results, otherwise returning the empty set. And then union froms do not get rewritten. We could implement a similar lowering rule for count, and I show an example of that here, which applies the same rewrites that I showed you on the previous slide. However, that would be a little bit misleading because count is actually expressed in Bonsai as a sum reduction over the map from an element to 1. And I don't have time to talk about all of the different rules in the paper, that we show in the paper, but we include rules for all of the different operators that we care about. And this is how we achieve fusion. Now, the way that we choose that we achieve pruning is via the generation of these always, maybe, and conversely never conditions. And to do so, we take some insight actually from the Halide compiler, which performs rather extensive symbolic interval analysis. And we realize that an always condition for a predicate P is the lower bound of the predicate, and a maybe condition is the upper bound of a predicate. You can also think of these as necessary and sufficient conditions. And Halide generates necessary and sufficient conditions via symbolic interval analysis, and we do the same. So we can apply rules like shown on the right here, where the lower bound of A and B is the lower bound of A ANDed with the lower bound of B, and similarly for the upper bound because AND is monotonic in its arguments. And so that gives us the first step in generating always and maybe conditions for this particular predicate. And we can similarly apply rules for A is less than or equal to B to generate the next step of lowering always and maybe. And now we've sort of hit some base cases. So the upper bound or lower bound of L and H these are non-varying values, and so they are just L and H. The upper bound and lower bound of X is actually given via our algebraic data type annotations. And so we can generate these pruning and inclusion conditions via the bounds annotations on the algebraic data type. And sort of the sort of key insight here is that these pruning conditions can be generated via symbolic interval analysis, and we call this predicate analysis. The results of pruning and fusion are that we get asymptotic speedups over sort of like linear scans, which is the existing alternative if you don't have a tree accelerated data structure for these queries. So on a number of filters, we evaluate on varying problem sizes on the x-axis, and we show the speed up over linear on the y-axis, and both of these are log scale. We show that we get rather massive speedups over linear scans on a variety of filters that database management systems fail to map to tree queries. But you'll see that there's sort of a tapering off at a certain point. And that's because these filters are not very selective. And so the runtime becomes write bound, where they are writing large amounts of outputs. And so to make these queries no longer write bound, we can instead query the count of the filter, where we're just accumulating the sum of the count. And we see that we can lift these speedups up even further. But there's still a tapering off. And that's because these queries have become read bound. They're reading too much data, and we get memory bound. However, if we extend the tree data structure to have the count augmentation of the subtree beneath it, we get near perfect asymptotic speedups for all of these queries, whether they're selective or not. And in the paper, we include a fusion ablation, as well as more advanced multidimensional filters and reductions and joint evaluations compared to database management systems. But with my remaining time, I want to talk about the exciting extension to predicate analysis, which is geometric predicate analysis. We started this project with the intent of accelerating queries like ray tracing and collision detection. And so there was always sort of an intent that this would be sort of a spatial query compiler. And I hope to motivate that with a sort of a simple extension to the range query example, which is suppose I have 2D space and I have a bunch of points in 2D space. And instead of selecting in a particular range, I want all of the points contained within a circle. In Bonsai, you can once again represent this as a simple filter over a set of objects such that a circle S contains the atoms of that set. And I can similarly build a tree on 2D space, wrapping points in bounding volumes recursively until I construct an entire tree. And then I can once again recursively evaluate on this tree, where yellow represents the maybe case, and green represents the always case of the filter predicate being true, and red represents pruning. So now you might say, well, okay, how do a predicate analyze contains? And if you're familiar with geometric implementations of circles and points, you might say, we'll just unwrap the implementation of contains and apply symbolic interval analysis to that. And that would actually work for circles and points. However, real-world geometry is considerably more complicated than circles and points. So suppose my base objects were actually triangle meshes. The implementation of whether a circle contains a triangle mesh is shown here. It's not important that you understand it. What is important is that you see that there's control flow, and it is non-trivial to analyze. And in fact, if you apply symbolic interval analysis to this, you actually get almost a nonsense result out of it that never prunes anything. And so we argue in the paper that for non-scalar operations, you need to reason explicitly about the operation semantics and not the implementations. And you can do so for all of these geometric operations. So for example, if I want to lower bound whether a geometry S contains a geometry X, the geometry S absolutely contains the geometry X if S contains the bounding volume of X, and that's because containment is transitive. Similarly, if I want the upper bound of whether S contains X, then that is that S intersects the bounding volume of X. And the intuition behind that is that if S does not intersect the bounding volume of X, it simply cannot contain the geometry X. And we include a number more geometric rules in the paper. The interesting results of these geometric extensions are what we like to term representative power without sacrificing performance. And what that representative power looks like is that I can implement ray tracing via 3 lines of code, maybe 2 if you have a longer code editor. I can implement closest point queries via a simple argument, and I can implement collision detection via 2 operations, the filter of a product. But the important thing about this representative power is that we do not sacrifice performance when compared to handwritten, hand-optimized code. So when we evaluate ray tracing versus the FCPW library, where orange is FCPW and blue is Bonsai, we get near exact parity. In fact, sometimes a little bit faster. This is showing runtime, not speed up. Similarly, for closest point queries, we get near perfect parity with a state-of-the-art library. And for collision detection, we actually see about a 1.5x speed up over the flexible collision library. We checked. This is not actually better pruning. It is that they have a slightly worse implementation, but not for pruning purposes. And with that, I'd like to leave you with the overview of the Bonsai compiler and a quick shout out that Bonsai is actually not alone, and it's part of a bigger system. So my co-author, Chris, presented Scion yesterday, which is all about extending the Bonsai project to have a physical layout memory specification language, which lets us truly get really peak performance for these spatial queries when compared to the state of the art, and achieve data independence for trees. So unfortunately, due to the ordering of conference talks, this talk was yesterday. But if you're interested, I encourage you to read the paper or watch Chris's the YouTube talk. And I'm happy to take any questions.
All right, again, so we'll take questions at the mics. Yep, Gilbert, one.
Thanks, this was really cool to see.
Thanks, Gilbert.
Oh, Gilbert Bernstein, University of Washington. Thanks, Pavel. 2 questions. Does it work on GPUs? And does it support any building of the tree hierarchies?
Excellent questions. So yes, it works. So Bonsai does not evaluate on GPUs. Scion does evaluate on GPUs. It's the same system. We evaluate on NVIDIA GPUs in Chris's paper. You're probably going to ask if we target the ray tracing cores as a follow-on. We do not. That would be possibly interesting follow-on work. And then, sorry, what was your second question?
But it does evaluate.
We do evaluate on GPUs.
Oh, cool.
Yes.
The second question is, can you do the tree builds?
Oh, yes. So neither Bonsai nor Scion implements interesting tree build algorithms. For comparison to the state of the art, we implement the exact same tree construction algorithms that they build, because the tree construction algorithm heavily impacts the performance of ray tracing code. We do think that's interesting future work to explore the domain space of build algorithms.
Cool.
Yeah, thanks.
Okay, so I'm going to ask Justin to be the last question. Sorry if you could keep it offline. And James, do you want to swap with AJ?
My email is on the slide if you want to send me an email with your question.
Thanks for the lovely talk. This is Justin Lubin, UC Berkeley. A question that I had is, does the lower bound or the upper bound for the contains operator fall out of some other definition, like automatically, or was that something that you specialized for the geometric containment?
So that's an excellent question. The honest answer is that I thought really hard and came up with rules that seemed right and derived the state-of-the-art in tree traversals. Collaborators who are significantly better at formal verification than me have since proved all of these rules to be correct. They have in fact found that some of the rules are not the tightest rules that they could be, though, so they can be optimized even further. But they are all correct. So
thank you.
Yeah, thanks. Here you go.
All right, thank you again for AJ. And next on our journey into relational databases, James will be talking about fusion for relational operations. Please, James.
Yes, thank you for the introduction. I am James Dong, and I'll be presenting my work on a compiler for fused relational operations on multisets. So first I'll give an overview of database systems, where relational databases are ubiquitous in modern software due in part to the flexibility of the relational model being suitable for many domains. Database systems take as input a query written in SQL and transforms it into a query plan composed of relational operators. For example, the query plan shown here is composed of a union operator on top, 2 joins below it, and a filter operation on the left. You may notice that this is not syntactically equivalent to the SQL query on the left, where the filter has been pushed down past the join as an optimization to reduce the amount of data processed. So after this query plan is constructed and optimized, the system then executes the query. Simple systems interpret these operators directly, but more sophisticated systems will perform some degree of compilation on the query plan before execution. We propose a system for compiling relational queries to fused code. Fusion here refers to operator fusion, or combining multiple relational operators into a fused implementation rather than materializing intermediate results. The 2 inputs to our compiler system are a query plan and the data structures to be used, such as the storage for the data structure, data tables, and indices. We obtain the query plan from our front end, which takes in the SQL query and produces an optimized query plan. The compiler system then takes these 2 inputs and produces efficient fused code. For many queries, fusion is necessary for optimal performance. The benefits of fusion are especially pronounced for cyclic queries, which show asymptotic improvements from fusion. The classic example of this is a triangle query shown here, where we have 3 vertices A, B, and C, and we join on the 3 pairs of edges between them. This query highlights a limitation of traditional query plans with binary joins, where a traditional query plan evaluates the query as a sequence of binary joins, each combining only 2 relations at a time. And no matter which 2 relations you choose to join first, the resulting joined relation has O of n squared tuples in the worst case. However, a fused multi-way join is able to achieve O of n to the 3 halves by simultaneously considering all 3 relations and avoiding the materialization of the O of n squared intermediate results. So 2 important lines of work in relational fusion are worst case optimal joins, such as Ingno's work in 2014, and pipeline fusion as used in Hyper in 2011. Worst case optimal join allows for fusion of inner joins, and it achieves optimal asymptotic complexity for the triangle join shown previously, as well as other cyclic joins. And in general, it can fuse any number of inner joins, as shown by the complex example on the slide, which has 4 different relations joined together. Fusion of inner joins, by the way, means simultaneously advancing through all joined relations, producing tuples as you go, and avoiding building large intermediate relations. On the other hand, pipeline fusion is restricted to only fusing a single pipeline, but is able to fuse together other operators than just inner joins. And so as a result, pipeline fusion is very good at fusing together unary operations such as filter and aggregation or group by, whereas worst case optimal joins are able to fuse any number of inner equijoins. But there are many other operations that cannot be fused by these systems. For example, inner equijoins are only one type of join used by relational queries. In addition to inner joins, we have 3 other types of joins, left, right, and full outer joins, which are collectively termed outer joins. And non-equijoins, in contrast to equijoins, allow for arbitrary predicates as their join condition, not just attribute equality. Finally, we would like to support set operations, such as union and intersection. Our compiler system extends fusion to all of these operations in the diagram. Having a unified compiler for all of these operations requires a powerful compilation scheme where most of the complexity comes from these new operators. So let's look at the overall flow of the system using our compiler approach. First, the front end translates a query written in SQL into a query plan, where we do not implement this, and we assume that this is already present. Next, the compiler will lower this query plan into a new intermediate language, ALIR, which represents fused operators as a series of nested loops. In order to compile these loops to native code, we first extract the loop domains and construct iteration machines, which are an auxiliary data abstraction used for generating fused loops. These are built on top of iteration lattices from Taco, and we generalize them to the expanded loop domains used in relational algebra with multisets. An additional input is the data structure specification, which specifies the data structure used for each input relation and the routine implementations necessary for code generation. Finally, given all of these inputs, the code generation algorithm will generate C++ code from the ALR and iteration machines, along with the data structure specification. So our system has too many details to be covered entirely. So in this talk, I'll focus on the lowering procedure and how the complex operators are represented in IR. For more details about iterations of machines, as well as the other parts not covered, please see our paper for more. So this talk is about compiling relational algebra. But another related algebra is tensor algebra. And let me talk a bit about the relationship between these two to get some key insights into our compilation approach. So on the slide, we have a few tensor algebra expressions. And here's part of the compute graph for attention. This is based on the IR used in JAX, where the top node here is a matrix multiplication, and the left node here is a ReLU. And here is a query plan for the left-hand relational algebra query, where there are some things that are similar between operators and tensor and relational algebra, where the structure of an inner join is actually very similar to the structure of a matrix multiplication. And so as a result, we could imagine using sparse tensor algebra techniques to compile relational algebra. And it turns out that this actually works quite well for the natural relational algebra, which is restricted to inner joins and sets, not multisets, without any complex operations. For example, this query on the slide here is in the natural relational algebra, but the relational algebra in modern databases is not linear. In particular, suppose we change the join here to a left join, or to a non-equijoin, or if we change the inputs to be multisets, where both of these modifications lie outside the scope of the traditional tensor algebra compilation techniques, where non-inner joins, such as left joins, require null handling, and multiset semantics changes the semantics of all operations and introduces some significant challenges to fused code generation. In order to handle the full generality of relational algebras used in real-world applications, we have developed a compiler system that is able to fuse all of these complex operations in a unified way. So let's look at how to represent an inner join in ALR. To capture the semantics of an inner join, we must first take the intersection of the B values in A and B. So this is performing the join operation. And the remaining loops will then extract the corresponding values of A and C from the A and B relations. Another key point is that these loops are abstract loops and are not tied to any particular data structure. For example, given the tuples for relation A, we operate using a coordinate tree that abstracts away the physical data structure. And if you look at the two attributes of A in the LAR, these two uses of A are linked, as shown in the coordinate tree. So as a result, the iteration of the second attribute, A.A, is restricted to only those values corresponding to the current iteration of A.B. And the coordinate tree abstraction is able to represent many types of real-world data structures, including row and column storage, tri-storage, hash tables, and B trees. Now, to represent outer joins, we require some new machinery. So let's look at how a full outer join is represented. The semantics of a full outer join, unlike an inner join, includes all elements from both joined relations, where the missing attributes, where no corresponding tuple exists, are filled in with null values, indicated by the empty set symbol. So to generate the LR for this outer join, first we look at the semantics of the full outer join, and we take the union of the corresponding attributes. And next, the values of A and C should produce null values when the B value does not exist in A and B respectively. And to represent this, we add a union with the null symbol, where the domain A.A union null produces a null value where B is not contained in A, and otherwise produces the corresponding values of A. We do the same thing for C, and we have the tuple generation unchanged. Now let's look at left and right joins. Like before, we write down the domain of B corresponding to the join semantics, where here we have simply A.B. However, the C loop should iterate over the C values corresponding to B, but the domain of B, if you can see, doesn't reference B.B at all, and so now B.C is not linked to anything. To fix this, we use the parenthesis operator to reintroduce B.B syntactically. This operator doesn't influence the actual domain of iteration, but it informs the code generator to insert branches to determine membership in B. Using this operator, we now see that the third loop B over B.C is now linked to B.B. As you can see, our approach uses simple loop domains that clearly expresses the resulting iteration behavior. This is supported by the linking behavior from the coordinate trees, which then ensures that the values correspond to actual tuples. Next, we'll talk about lowering. The input to our lowering procedure is a physical query plan. A physical query plan contains information about what implementation should be used to execute each operator. Our lowering process consists of rules for each operator, which means that the physical query plan specifies which rules should be used to lower each operator. We implement this by using a physical query plan with annotations. The perm rule at the top means to permute the loop ordering into a given new ordering, and the precomp rule means to precompute the given subtree into a temporary relation before proceeding with the rest of the query. We note that our work has fewer pipeline breakers, which require precomp annotations than hyper, but some operations such as aggregations remain pipeline breakers in our work. These precomp annotations form an explicit fusion boundary, shown in orange, where the operators in each orange circle are fused together, but fusion does not occur across circles. As we'll see, the mechanism for fusion is accomplished by the lowering rules, whereas the decision of where fusion occurs is decided by the query plan. By performing fusion during the lowering process, we gain the advantages of both the high-level representation of query plan operators and the low-level loop representation without losing the benefits of each. On a high level, we have locality of annotations on operator subtrees compared to the global scheduling commands of Taco. And on a low level, we have greater flexibility since we have access to the low-level loop representation during lowering. Now let's see how our compiler lowers a query plan into LAR. We take as input a query plan with annotations that informs the lowering process, where lowering proceeds bottom up using lowering rules for each operator. Let's call the results of the precomputed section T, and the rest of the query then uses T as a normal relation. We omit the lowering of the actual content of T for this talk, but iteration over T, where we just treat this as a standalone relation, this is lowered as shown, where you may notice that there's an extra dupes loop. This is covered in detail in our paper, but in a nutshell, it's used to handle multi-set semantics in general. We proceed bottom up, so we lower the union of A and B as shown here, simply taking the union of corresponding attributes. Next, we need to lower the top join operator, where going in detail, we are doing an inner join. So we first produce the join condition by taking the intersection of the corresponding attributes, which produces the domain shown here. Next, we copy the domains for the remaining A and C attributes. And for dupes, we take the Cartesian product, and this is according to the multi-set semantics of join. Next, we merge the output tuples. Finally, there's a perm annotation on the top, and so we will apply the perm annotation by permuting the loop ordering. Next, let's look at the performance of our system. In this talk, I'll only cover a few of the key results on fusion, but our paper has several more key results, such as a data structure comparison, where here we have the results for the triangle query from before. So here we have input size on the left, on the x-axis, and runtime on the y-axis, where lower is better. And in this log-log plot, we see that our approach has an asymptotic speedup compared to the other systems which use binary joins. Next, let's look at the results from the LSQB benchmark, which uses a diverse set of operations, including cyclic joins, union operations, and anti-joins. And we see that for Q2 and Q4, we are roughly comparable to Hyper, which uses pipeline fusion, as well as free join, which is a relatively recent implementation of worst-case optimal join. You'll notice that the Q4, there's a small caveat where, due to their output representation, they're not directly comparable, but in our paper, we have a detailed comparison where we show that we are, in fact, comparable. Q6 and Q9, where Q9 has a cyclic anti-join, and otherwise it's the same query. So significant speedups from our approach, where our compiler approach has the flexibility to reorder loops to defer iteration, leading to a 6 and 14 times speedup. Please see our paper for a more expanded evaluation, including TPCH results and a data structure comparison. So in conclusion, we've shown how to fuse together these complex relational operators. And yeah, thank you for coming, and I'll open for questions.
Okay, again, thank you, James. And let's take questions up here at the microphone. Well, while people wait, I did want to know, can you expand a little more about free join? Why is the data incomparable, and what did it take to incorporate?
Yes, of course. So here, the free join essentially has what they refer to as a factored input and output representation, where essentially they factor like some amount of the multi-set semantics. And so as a result, their output representation is also factored, and so they are able to basically completely skip the multi-set semantics. And so we actually also implemented a factored representation, and we show that our approach is very comparable.
Very cool.
Great talk. This is Yi Hong from UW. So I have two questions. The first question is, have you compared with Umbra, which is a successor to Hyper?
Sorry, which?
Umbra.
Oh, yes. We were aware of the system. We did not have time to implement a direct comparison.
Okay. My second question is, in my experience, worst case optimal join usually spends most of the time in like building the indices. Are you doing something like fast for that, or are you
applying for so the results shown here omit all index building costs. Right? Okay. So this is directly the speed of the actual join implementation.
I see. And what kind of indices do you use in this
yes.
paper?
We use essentially a tri-representation for most of the results. We also have an expanded data structure comparison in the paper.
Thank you.
Okay. Thank you again for James. So we are at, I think, maybe the very last talk of PLDI. So no pressure, Robert. He's right behind you. But let's bring it home strong. So we are going to continue our discussion here, database systems, and now we're going to look at predicate pushdown, common optimization in databases, and how that can be applied to user-defined functions. So Robert will be telling us about that.
Test. Oh, great. All right, welcome to the last talk of the conference. I will be brief, try to be as brief as possible so that y'all can go hang out afterwards. But let me start the. Wait. Okay. Alrighty. I'm Robert from UT Austin, and today I will present our paper, Optimal Predicate Pushdown Synthesis, with this is joint work with Eric, Dishan, and Ishel. Now, let's first consider this common scenario where we have a big chunk of data, which we feed into a potentially expensive computation. And at the end, after we obtain the output, we apply a filter to it. Now, the question is, what happens if most of the output just gets thrown away by the filter? In that case, why bother running the expensive computation at all? Well, a further question is, can we filter most of the data out before we even get to the computation? It turns out this is a well-known technique called predicate pushdown. It talks about moving filters before costly operators. It is also standard and well understood for SQL and relational algebra. And as covered in the previous talk, we move filters before joins all the time. It's considered pretty much solved for relational database. However, such classic pushdown falters at modern data pipelines written in general purpose programming languages like Python or Scala. The culprit is user-defined functions, UDFs, that are essentially arbitrary stateful code that users write alongside these relational operators. Because these query optimizers treat UDFs as black boxes, they essentially throw up their hands and say, not my problem, whenever they get to these things. Let's take a look at a concrete example of what these pipelines look like. Here, we read data from a CSV file into a data frame, and then we drop null values from it. After that, we perform a per group aggregation that essentially computes the top 2 scores of each team. After we obtain the output data frame, we merge it with a team's data frame. At that point, we apply a filter to the combined table that essentially keeps only rows with both top 2 scores above 90. At the end, we write to a CSV file. Now, let's focus on the last filter here and try to push it back all the way up through the pipeline. The first step is easy because we can push it to before merge because the filter only concerns attributes from the tops table. But here we run into a wall because classic methods treat UDFs like top 2 as a black box, so they cannot relate the filter to the input table. But what exactly is top 2? Let's take a look. As I said before, UDFs can be arbitrary stateful code, and I would like to highlight 3 things that make UDFs hard. The first being internal state. In this case, top 2 tracks the first and second variables that hold the running top 2 scores. The second being that some UDFs tend to involve whole group reasoning, which is also in this case, which is also the case here, as any top 2 score only makes sense relative to others in the same group. Lastly, UDFs tend to have rich control flow in the form of loops and branching conditions. In this case, what we ideally want is to be able to split up this original filter P into 2 components, one that happens before the aggregation using top 2, that does the heavy lifting to filter out all the irrelevant rows, and another component that happens in place after the aggregation that serves as the remaining cheap validation to ensure semantic equivalence. As a result, we are able to preserve semantics while requiring far less work on the part of the top 2 UDF. Now, with the UDF unblocked for pushdown, let's go through the pipeline again to carry out pushdown end to end. Again, we're able to very easily push the original filter P through merge, and then we're able to split it up into Q and P prime. And we can further move Q up to before drop in A because the score greater than 90 condition already rules out nulls. So yeah, that's the idea. And here's our goal. Our goal is to be able to do the following. For arbitrary code in the form of UDFs, we want to efficiently compute verified and optimal pushdown at scale, pushdown splits. Here we have 3 concrete criteria. The first one is the correctness condition. We would like to rewrite the original pipeline into the optimized version where the predicate P is split into Q and P prime. And the next 2 conditions involve talks about optimality. We want Q to be as strong as possible because we want to filter out as much data as possible. Second, we want P prime to be as cheap as possible because we want to minimize work as well as to reduce redundancy with Q. So in the most ideal case, we want P prime to just be true, which is like nothing. Before we could get to automatically finding these pushdown splits, we first need to be able to check this equivalence. Here, we first recognize that predicate pushdown is fundamentally a program correspondence problem, where the original and optimized pipelines need to be related step by step. This is exactly what bisimulation is for, and we establish equivalence through a so-called bisimulation invariant I that relates the original and optimized runs at each intermediate step and at the very end. So here we see that I should hold at the beginning with the initial 2 states S0 and S0 prime. And as we step through the data frame, either keeping or dropping rows, I should keep holding. For example, when a row is kept, both the original and optimized runs step forward, and I should also relate the new pair of states. And if a row is dropped, only the original run steps forward because that row is filtered out in the optimized run. I should hold despite that. And so on and so forth until we exhausted the rows in the data frame. At this point, I should ensure that the 2 residual filters, P and P prime, that they agree on the 2 final states, S4 and S2 prime. And in the case where both P and P prime accept their respective final state, the two final states should be equal. And given the system, using this notion of equivalence via bisimulation, we're able to derive a set of 4 VCs that allow us to check whether I holds initially, whether it's preserved by every row, and whether it implies final state agreement. First, we have the initial condition that says I should hold on the initial states. And then we have a VC corresponding to the case where a row is kept, where Q holds on R and both the original and optimized run step, and then I should keep holding. The third concerns the case where a row is dropped, Q fails on R, and then only the original run steps, I should hold. Lastly, we have the final state agreement VC that says that I should imply one of two things, either both P and P prime hold on their respective final state and the final states are equal, or both of them reject the final states, in which case we don't care about what those final states are concretely. Well, looking at this system of formulas, one may wonder, why not use a CHC solver for this? Because it's a very common approach when you can encode these formulas as constraint horn clauses, and so you can solve for the unknowns using off-the-shelf solvers. Well, we don't do that here because we can't. There are two reasons. One is that if you look at the third VC, both Q and I, the two unknowns, appear positively, which means that these VCs are not in horn form. But even if they were, a CHC solver doesn't guarantee us the optimality that we want, namely that we want the strongest pre-filter Q and the cheapest residual filter P prime. So as a result, we have a hard predicate synthesis problem that require some custom synthesis algorithm that we developed. We use 3 key ideas in our synthesis algorithm to make sure that it's efficient. Namely structured search, unrealizability certificates, as well as root cause guided predicate repair. Let's begin with structured search. What I mean by that is that we untangle this 3-way coupled search into a layered pipeline where we first enumerate Q from strongest to weakest, and then for a given Q, we try to find the strongest by simulation invariant I that establishes its correctness. And only after that do we finally look into finding the weakest P prime. I would like to highlight 2 salient aspects of this flow here. The reason why we're able to isolate Q and I first before P prime is because only the first 3 VCs concern them. This allows us to focus our attention on what matters most. Because if you think about it, we care about the strength of Q the most, in a way. And also, we want to find the strongest I first because we know that given the shape of the fourth VC, where I occurs in the implicant, we know that if the strongest I doesn't suffice to show correctness for any valid, any P prime, then no other I would be able to do so. So we're able to terminate quickly. For termination, it's necessarily the case that we draw Q, I, and P prime from their respective finite predicate universe, which we construct using atoms extracted from the UDF as well as the original filter. And because we enumerate Q in order of strength, as long as whenever we find a valid Q paired with a weakest corresponding P prime, we already obtained the optimal solution. The next component to our algorithm is this unrealizability checking feature, where we need this because obviously for a lot of Q candidates, they could not be paired up with any valid invariant because they could be too strong, meaning that they would drop rows that could change the result beyond recovery by any residual filter. In this case, we would like to prevent wasting work on doomed paths, so we would like to know if Q is unrealizable at the start before exploring its whole subtree. We do this, we're able to achieve early termination by maintaining lower and upper bounds on the bisimulation invariant throughout the algorithm. Here concretely, we have I min, which is lower bound, which describes what must hold for any any feasible invariant for the particular Q. And we have I max that describes the most I can hold for any such invariant. And this bound will shrink as the algorithm progresses. If at any point the bounds cross, that means no invariant can work for the given queue. So we deem it as unrealizable and we skip the whole subtree. Lastly, we have this notion of like root cause guided predicate repair, where we don't just blindly try to fix feasible candidates. We instead look at the concrete failure modes, for example, for candidate queues. In this case, we check which VCs failed concretely and on what concrete row. And then we see if the VC failed because of keeping the row R or dropping the row R. If it failed because of keeping R, then we adjust Q to drop that row. If it failed because it dropped the row, then we adjust Q to keep it. And then after we obtain the repaired Q in this way, then we feed it back into the loop. Importantly, this step, such steps not only drops that particular candidate Q, but it also eliminates all candidates involving those offending atoms. Given all these ingredients, we implemented all of them in a tool called Pusharoo and evaluated it on a suite of 150 benchmarks involving real-world UDFs. And it turns out that Pusharoo is really good. It is able to solve and infer optimal push-down splits for 100% of them. And it's able to do so very quickly. The median synthesis time is 1.6 seconds, and it has a big impact on the end-to-end runtime of the pipelines. We see on average that the pipelines are sped up by 2.4 times, and at most we saw 2 orders of magnitude of speedups. And it's also good to highlight that prior work applies only to less than 15% of these benchmarks. So we're not even talking about like actually solving them. So thank you so much for tuning into my talk. Please check out the paper for more details. Here's the QR code for that, and please feel free to contact me for any questions.
All right, once again, we will take questions at the microphone, please. Oh man, everyone is immediately up asking questions, please.
Very nice work. I'm curious if you're able to push down user-defined functions past arbitrary user-defined functions, and if you'd looked at like parallel streams in, say, Eclipse collections or Java, the standard library. Thanks.
I guess you meant pushing filter predicates down through the UDFs instead of pushing UDFs down through UDFs.
Well, the UDFs pass other UDFs, because you can imagine a predicate that also includes a UDF, right? That maybe filters things that are increasing based on the state. Would that be possible?
Yeah, so that's definitely not the focus of this work. We don't quite model that. We really consider filters as stateless in this work. So, but it could definitely be an interesting follow-up work to extend to that.
Okay, and the parallelism?
Yeah, I think that definitely, our tool definitely applies to that. I think we can perform pushdown with Pusharoo in each chunk of the work, and recombine them if order doesn't matter. Yeah.
Thank you.
Thank you.
Hi, Justin Lubin, UC Berkeley. Thanks for the great talk. One thing I was curious about is the bisimulation invariant data dependent, or are you trying to prove that the programs are going to be equivalent for all possible input data sets? Seems like you might be able to get some like coarser notion of equality.
Yeah, it's, I forgot to mention that. Let me go back. I forgot to mention that all the VCs are universally, like the S and R variables are all universally quantified.
And have you thought about making it like data dependent?
Yeah, in fact, during development of this work, at various points it seemed to be the case that having the users provide some like assumptions or on the shape of the input data would help unlock more opportunities, but we decided that for now we want to have a cleaner theory and just keep it at this. But that's definitely an interesting follow-up work. Yeah.
Thanks.
Hi, AJ Root from Stanford. Great talk and cool project. I just wanted to ask, so in database management systems, there are some cases where predicate pushdown is actually not preferred. Like you would not push a predicate down past a join in the case of like the predicate being extremely expensive, like some sort of like regex expression on strings. Yeah. Do you ever see in your benchmarks that predicate pushdown actually like decrease or reduces negatively impacts runtime?
Absolutely.
Does that happen in your benchmarks?
Yeah, absolutely. There are cases where we see like negative performance increase.
Okay. So do you think there's a way like to incorporate some sort of cost model of like what optimality means to make like a cheap predicate pushdown?
You touch on a really good point. Definitely. We can definitely involve all the prior work in the database community on cost models. Currently, we only use logical strength as our sole criterion, but that's all because we want like a elegant theory for a start. But yeah, we can plug in, like for example, looking at the number of like the concrete shape of the predicate, for example, or we can take some off-the-shelf like cost model learned previously in our domain. So yeah, it's definitely possible.
All right, cool. Thanks.
Mm-hmm.
And I wanted to mention that Robert is interested in internships or down the line possibly employment, so talk to him about that as well. And with that, I think we can close out PLDI 2026. I hope to see you all in Atlanta next year.